Two things fill the soul with ever new and increasing admiration and awe, the starry sky above me and the moral law within me. Immanuel Kant. The Milky Way, our galactic home. In the vast expanse of the universe, where billions of galaxies weave together the intricate fabric of space and time, we find ourselves nestled within one grand structure, a cosmic island of stars, dust, and dark matter. This island, which we call the Milky Way, is not just our home but a testament to the mysteries and wonders that the cosmos holds. The Milky Way is a spiral galaxy, a majestic whirlpool of stellar systems, bound by the invisible force of gravity, which curates the dance of billions of stars. When we look up into the night sky, the faint glow of the Milky Way stretches across the heavens like a celestial river, a glimpse of our galaxy's plane viewed edge-on from within. To the naked eye, it appears as a luminous band, but in reality, this sight is but a fraction of the full grandeur that extends across 100,000 light-years. At the heart of it lies the galactic core, a dense region swarming with stars, gas, and a supermassive black hole known as Sagittarius A*, around which everything orbits in serene synchrony. A galactic symphony of stars. Our galaxy contains anywhere from 100 to 400 billion stars, each a fiery furnace of nuclear fusion, churning elements into existence. These stars come in myriad forms, from the smallest, dimmest red dwarfs to the most massive and luminous blue giants. Every star, including our own Sun, is part of a much larger system, bound within the galactic disk, a flat plane of stars, planets, and cosmic dust that revolves around the central bulge. The stars in the Milky Way form patterns, structures that astronomers have painstakingly uncovered over centuries of observation. One of the most striking features is the spiral arms, curving streams of stars and gas that swirl outward from the center, like the arms of a cosmic octopus. These arms are sites of intense star formation, where gas clouds collapse under gravity, igniting new stars that will burn for billions of years. But the story of our galaxy is not only about the bright stars we can see. There is another component, a dark and invisible one that holds the key to the very structure of the Milky Way. This is dark matter, a mysterious form of matter that does not emit, absorb, or reflect light, yet exerts gravitational influence on all visible matter. It forms a vast halo around the galaxy, anchoring the stars and gas in place, and ensuring the stability of the spiral arms. Without dark matter, our galaxy's structure would unravel, and the stars would be flung into the depths of intergalactic space. The galactic center, the heart of darkness. At the core of the Milky Way lies a region shrouded in mystery and danger, the galactic center. Hidden within this crowded and chaotic environment is Sagittarius A*, a supermassive black hole weighing in at over 4 million times the mass of our Sun. This black hole, though invisible, exerts a powerful gravitational pull on the stars, gas, and dust that surround it, shaping the orbits of objects within its sphere of influence. Sagittarius A** is a silent predator, consuming anything that ventures too close. Yet, it is not alone. Surrounding it are dense clusters of stars, packed so tightly that they orbit one another in a cosmic dance of gravitational interactions. This region is also home to strange phenomena, massive star-forming clouds, powerful jets of radiation, and enigmatic objects that defy our understanding of physics. Despite the intense gravitational forces at play, the central bulge of the Milky Way is a stable and long-lasting feature, holding the galaxy together as it evolves over billions of years. The Milky Way's evolution. The story of the Milky Way is not one of stasis, it is a tale of continuous evolution and change. From its birth over 13 billion years ago, the galaxy has been shaped by collisions, mergers, and the relentless forces of gravity. In its early days, the Milky Way was much smaller, a proto-galaxy formed from the collapse of vast clouds of gas and dark matter. Over time, it merged with other galaxies, growing in size and complexity. Even now, the Milky Way continues to interact with its neighbors. The most notable of these interactions is with the Andromeda Galaxy, a fellow spiral galaxy located 2.5 million light-years away. Though Andromeda seems distant, it is on a collision course with the Milky Way. In about 4.5 billion years, the two galaxies will merge, creating a new, larger galaxy, an event that will dramatically reshape both structures. But the Milky Way's evolutionary path is not just shaped by external forces. Within the galaxy, stars are born, evolve, and die in a cosmic cycle of creation and destruction. The massive stars that form in the spiral arms live short, violent lives, ending in supernova explosions that seed the galaxy with heavy elements, carbon, oxygen, iron, that are essential for the formation of planets and life. These elements are recycled into new stars and planets, perpetuating the cycle of cosmic evolution. A galactic symphony of life and death. The Milky Way is a vast ecosystem where the life and death of stars create an ever-evolving tapestry. In the spiral arms, clouds of hydrogen gas, primordial material left over from the birth of the universe, serve as stellar nurseries. Here, gravity slowly coaxes clumps of gas to collapse, igniting the nuclear fusion that turns a protostar into a full-fledged star. These newborn stars light up the surrounding gas, carving out glowing nebulae that stretch for light years. Some of these stars, like our Sun, will burn steadily for billions of years, providing a stable environment for planets to form and perhaps for life to emerge. Other stars, far more massive, live shorter, more dramatic lives. These behemoths burn through their nuclear fuel at an astonishing rate, shining millions of times brighter than the Sun but exhausting their energy in mere millions of years. When these massive stars die, they go out with a bang, a supernova explosion that outshines entire galaxies for a brief moment. These cosmic fireworks not only mark the end of a star's life but also the beginning of a new chapter for the galaxy. The supernova disperses elements forged in the heart of the star, carbon, oxygen, silicon, and iron, into the surrounding space. These elements are the building blocks of planets and life itself. Without the death of these massive stars, there would be no Earth, no us, no life as we know it. Every atom in our bodies, every molecule in the air we breathe, was forged in the heart of a dying star billions of years ago. The galactic halo, a dark enigma. While the visible stars and nebulae form the bright, photogenic parts of the Milky Way, they are only a small fraction of the galaxy's total mass. Surrounding the Milky Way like an invisible veil is the galactic halo, a vast region of dark matter and scattered stars that extends far beyond the visible disk. The halo is home to ancient globular clusters, spherical collections of stars that are among the oldest objects in the galaxy. These clusters, containing hundreds of thousands of stars, orbit the galaxy's center in eccentric, elongated paths. But the halo's most mysterious component is dark matter. This enigmatic substance, which does not interact with light in any way, makes up the majority of the galaxy's mass. Though we cannot see it, dark matter exerts a powerful gravitational influence on the stars, gas, and dust in the Milky Way. Without dark matter, the stars in the outer regions of the galaxy would fly off into intergalactic space. Its presence is the invisible glue holding the Milky Way together, shaping its structure and governing its rotation. Despite its importance, dark matter remains one of the greatest unsolved mysteries in modern astrophysics. We know it exists, yet we don't know what it's made of. Physicists have proposed various candidates for dark matter, from weakly interacting massive particles, WIMPs, to axions, but so far, no definitive answer has been found. The search for dark matter continues, and unraveling its nature could unlock new insights into the fundamental workings of the universe. The Milky Way's place in the cosmos. Though the Milky Way is a massive structure, spanning 100,000 light-years and containing hundreds of billions of stars, it is but a single galaxy in a universe filled with countless others. Our galaxy belongs to a small group of galaxies known as the Local Group, which includes Andromeda and several dozen smaller satellite galaxies. Beyond the Local Group lies the Virgo supercluster, a vast network of galaxies that stretches across hundreds of millions of light-years. The Milky Way, like all galaxies, is constantly moving through the cosmos. It is not static, but is carried along by the expansion of the universe, which drives galaxies away from one another at ever-increasing speeds. This cosmic expansion, first discovered in the early 20th century, has profound implications for our understanding of the universe's future. As space itself stretches, galaxies like the Milky Way will grow more isolated from one another, separated by the expanding voids of intergalactic space. And yet, even as galaxies drift apart, the Milky Way is on a collision course with Andromeda. This future galactic merger, set to occur in about 4.5 billion years, will reshape both galaxies into a single, massive elliptical galaxy. Though the individual stars within the galaxies are unlikely to collide, the gravitational interactions will send them into new orbits, creating a chaotic yet beautiful spectacle of stellar rearrangement. Over time, this new galaxy, sometimes referred to as Milkomeda, will settle into a new equilibrium, its shape and structure forever changed. The search for life in the Milky Way. One of the most profound questions facing humanity is whether we are alone in the universe. The Milky Way, with its billions of stars and even more numerous planets, presents tantalizing possibilities for the existence of life beyond Earth. In recent years, astronomers have discovered thousands of exoplanets, planets orbiting stars other than our Sun, many of which reside in the habitable zone, where conditions might be right for liquid water and, by extension, life. Among these exoplanets, some stand out as particularly intriguing candidates for hosting life. Planets orbiting red dwarf stars, the most common type of star in the galaxy, are of special interest. Though these stars are smaller and cooler than the Sun, they burn for tens of billions of years, providing a stable environment for life to evolve. However, red dwarfs are also known for their intense stellar flares, which could strip away the atmospheres of nearby planets, posing a challenge for life as we know it. Despite these challenges, the search for extraterrestrial life continues. Projects like the Search for Extraterrestrial Intelligence, SETI, aim to detect signals from alien civilizations, while missions like NASA's Kepler and TESS telescope search for Earth-like planets around distant stars. The discovery of even microbial life elsewhere in the galaxy would revolutionize our understanding of biology, evolution, and our place in the cosmos. The future of the Milky Way. As we look ahead to the distant future, the Milky Way will continue to evolve, shaped by the forces of gravity, star formation, and cosmic interactions. In billions of years, when the Sun has long since burned out and the Milky Way has merged with Andromeda, the galaxy will look very different from the one we see today. New stars will continue to form, old stars will die, and the cycle of cosmic creation and destruction will go on. Yet, the long-term fate of the Milky Way, and indeed, the entire universe, remains a mystery. Some theories suggest that the universe will continue to expand indefinitely, with galaxies drifting farther apart until they are too distant to see. In this scenario, the Milky Way will become increasingly isolated, its stars gradually burning out and fading into darkness. Other theories propose a more dramatic end, with the expansion of the universe reversing into a Big Crunch, or the fabric of spacetime itself tearing apart in a Big Rip. Whatever the future holds, the Milky Way stands as a testament to the beauty, complexity, and mystery of the universe. It is our home, our cosmic address, a place of wonder and discovery. As we continue to explore its depths and unravel its secrets, we are reminded of the incredible journey we are all on, one small part of a grand cosmic story that has been unfolding for billions of years, and will continue for billions more. The stellar neighborhood, our place in the galactic suburbs. Within the vast and sprawling structure of the Milky Way, our Sun occupies a modest position. It resides in the Orion Arm, a minor spiral arm between the larger Sagittarius and Perseus arms. Often referred to as one of the galaxy's suburbs, this region is relatively quiet and stable compared to the crowded, chaotic center. Here, stars are spaced far enough apart that they can maintain stable planetary systems without being disrupted by the gravitational influence of their neighbors. Our solar system lies about 27,000 light-years from the galactic center, placing us in a location where we have a unique perspective. From here, we can observe the galaxy's structure, its grand spiral arms, and the dense clusters of stars that populate the central bulge. But the galactic center is not easily visible to us. It's obscured by dense clouds of gas and dust, which block much of the visible light that would otherwise reveal its hidden wonders. Despite our suburban location, we are far from isolated. The Sun is part of a local stellar neighborhood, a loose collection of stars that drift together through the galactic disk. These stars are our nearest neighbors in the cosmic sense, and some of them, such as Alpha Centauri and Proxima Centauri, lie only a few light-years away. Yet even our closest neighbors are separated by vast distances. It would take over 4 years for light, the fastest thing in the universe, to travel from Earth to Proxima Centauri, a distance that is almost incomprehensible in human terms. Among these stellar neighbors, astronomers have discovered planets, worlds orbiting distant suns, just as our planets orbit the Sun. Some of these exoplanets are rocky, like Earth, and reside in the so-called habitable zone, where conditions might be favorable for life. The discovery of these worlds has fueled our imagination and raised profound questions about whether life exists elsewhere in the galaxy, quietly thriving under alien skies. The birth and death of stars, a cosmic life cycle. Stars, like all things in the universe, are not eternal. They are born, live out their lifetimes, and eventually die in a process governed by the relentless march of cosmic time. The Milky Way, with its spiral arms teeming with gas clouds, is a galaxy rich in star formation. In regions like the Orion Nebula, dense clouds of gas and dust collapse under their own gravity, igniting the nuclear fusion that powers stars. This process has been occurring for billions of years, and it will continue for billions more, as long as there is raw material to fuel the creation of new stars. The life cycle of a star depends on its mass. Small stars, like red dwarfs, burn their fuel slowly and can live for trillions of years, far longer than the current age of the universe. These stars are the cosmic survivors, outliving their more massive counterparts by orders of magnitude. In contrast, the most massive stars burn through their fuel quickly, living fast and dying young in spectacular supernova explosions. These explosions, though catastrophic, play a crucial role in the cosmic ecosystem by dispersing heavy elements into space, elements that will one day form new stars, planets, and potentially life. Our Sun, a relatively small star by cosmic standards, is about halfway through its 10 billion-year lifespan. In about 5 billion years, it will exhaust the hydrogen in its core and begin to fuse helium, swelling into a red giant in the process. When this happens, the Sun will engulf the inner planets, including Mercury and Venus, and render Earth uninhabitable. Eventually, the Sun will shed its outer layers, leaving behind a hot, dense core known as a white dwarf, a stellar remnant that will gradually cool and fade over trillions of years. The death of massive stars, however, is far more violent. When a massive star reaches the end of its life, its core collapses under the force of gravity, triggering a supernova explosion that releases more energy in a few seconds than the Sun will emit in its entire lifetime. The core may then become a neutron star, an incredibly dense object packed into a space no larger than a city, or, if the star is massive enough, a black hole, an object so dense that not even light can escape its gravitational pull. The galactic disk, a stellar highway. The Milky Way's disk is its most prominent feature, a flat, rotating plane where the majority of the galaxy's stars, gas, and dust reside. It is in this disk that the spiral arms unfurl, creating a grand, swirling pattern that has captured the imagination of astronomers for centuries. The disk is not uniform but instead varies in thickness, becoming thinner near the edges and thicker as one approaches the galactic center. The stars in the disk orbit the center of the galaxy in orderly, nearly circular paths, like cars on a cosmic highway. These stars, including our Sun, take hundreds of millions of years to complete a single orbit around the galactic center, a journey that spans vast distances. Our Sun, for example, takes about 230 million years to complete one orbit, meaning that it has circled the galaxy about 20 times since its formation. During this time, the Earth has experienced dramatic changes, from the formation of continents to the rise and fall of entire species. The galactic disk is also home to vast quantities of gas and dust, the raw material from which stars and planets are born. This interstellar medium is not evenly distributed but instead forms clouds of varying density. In some regions, the gas is dense enough to collapse under its own gravity, triggering the birth of new stars. In other regions, the gas is more diffuse, creating vast empty spaces between the stars. Over time, the gas in the disk will be used up, and the rate of star formation will slow, eventually coming to a halt. Galactic cannibalism, the fate of satellite galaxies. The Milky Way, like all large galaxies, is not a solitary structure but is surrounded by smaller satellite galaxies that orbit it like moons around a planet. Some of these satellite galaxies are visible from Earth, such as the Large and Small Magellanic Clouds, which can be seen with the naked eye from the southern hemisphere. These galaxies, though small, play an important role in the life of the Milky Way, supplying it with fresh material for star formation. However, the relationship between the Milky Way and its satellites is not one of peaceful coexistence. Over the course of billions of years, the Milky Way has grown in size by consuming smaller galaxies in a process known as galactic cannibalism. These mergers are violent events, with the smaller galaxy being torn apart by the gravitational forces of the larger one. The stars from the smaller galaxy are absorbed into the Milky Way, adding to its mass and altering its structure. Even now, the Milky Way is in the process of devouring several satellite galaxies, including the Sagittarius dwarf galaxy, which is currently being pulled apart and assimilated into the Milky Way's disk. These mergers will continue for billions of years, gradually increasing the size of the Milky Way and reshaping its structure. The ultimate destiny of the Milky Way. As we peer into the future, the fate of the Milky Way seems inextricably linked to its impending collision with the Andromeda Galaxy. Though the two galaxies are currently separated by millions of light-years, they are on a collision course that will culminate in a dramatic merger in about 4.5 billion years. This event will be one of the most significant in the history of the Milky Way, reshaping its structure and triggering a burst of star formation as gas clouds are compressed and stars are born in the resulting tidal forces. Though the merger will be a slow and graceful process, taking hundreds of millions of years to complete, it will forever alter the face of the galaxy. The spiral arms of both galaxies will be disrupted, forming a new, elliptical galaxy that will bear little resemblance to the grand spirals that preceded it. The central black holes of both galaxies will also merge, creating a single, supermassive black hole at the heart of the new galaxy. In the distant future, the universe itself may grow cold and dark, with galaxies becoming isolated as the expansion of space accelerates. Yet, even in this far-off time, the Milky Way will remain a testament to the grandeur and mystery of the cosmos, a place of wonder, where stars are born, worlds form, and the search for meaning continues. The Milky Way's dark matter halo, the invisible scaffold. While stars, gas, and dust make up the visible components of the Milky Way, they account for only a fraction of its total mass. Surrounding the galaxy, like an invisible cocoon, is the dark matter halo, a vast, spherical region that extends far beyond the visible edge of the galaxy. Dark matter is the unseen substance that permeates the universe, exerting a gravitational influence on visible matter without emitting or interacting with light. The dark matter halo plays a critical role in shaping the Milky Way. Without it, the gravitational pull from visible matter alone would be insufficient to hold the galaxy together. The stars, gas, and dust in the outer regions of the galaxy would simply drift away into intergalactic space. It is dark matter that ensures the galaxy's stability, providing the additional gravitational force necessary to bind its components into a cohesive whole. Despite its importance, the exact nature of dark matter remains one of the most profound mysteries in astrophysics. Astronomers have been able to infer its existence through the motion of stars and galaxies, but they have yet to detect dark matter directly. It does not interact with electromagnetic forces, meaning it neither emits, absorbs, nor reflects light. Instead, dark matter's presence is felt through its gravitational influence, which affects the motion of stars in the Milky Way's outer regions, causing them to orbit faster than would be expected if only visible matter were present. Dark matter's elusive nature has prompted numerous theories about what it could be. Some scientists propose that it is made up of weakly interacting massive particles, WIMPs, while others suggest more exotic particles, such as sterile neutrinos or axions. Despite decades of research and experimentation, dark matter continues to elude direct detection, remaining one of the universe's greatest unsolved puzzles. Understanding dark matter's true nature could unlock new insights into the fundamental laws of physics and the origin of the universe itself. The galactic core, a gateway to the unknown. At the very heart of the Milky Way lies one of the most enigmatic and extreme regions in the galaxy, the galactic core. This dense and energetic region, located some 27,000 light-years from Earth, is home to a supermassive black hole known as Sagittarius A star. With a mass equivalent to more than 4 million suns, Sagittarius A* exerts a powerful gravitational pull on everything around it, including stars, gas, and dust. The existence of a supermassive black hole at the center of the Milky Way was first inferred through the observation of the orbits of stars near the core. These stars move at incredible speeds, indicating the presence of an extremely massive, yet invisible, object. Sagittarius A* fits the bill perfectly, a black hole so dense that not even light can escape its gravitational grip. Although Sagittarius A* itself is invisible, its influence can be seen in the material that surrounds it. Gas and dust are drawn into the black hole's accretion disk, where they are heated to millions of degrees as they spiral inward. This process releases enormous amounts of energy in the form of X-rays and radio waves, which can be detected by telescopes on Earth. The area around Sagittarius A* is also home to some of the most extreme phenomena in the galaxy. Massive stars, packed tightly together, orbit the black hole in a frenetic cosmic dance, their paths distorted by the black hole's intense gravitational field. Occasionally, a star will stray too close to the black hole, where it is ripped apart by tidal forces, its remnants consumed in a violent burst of radiation. This process, known as spaghettification, is one of the most dramatic displays of the power of black holes. Despite the danger posed by the black hole, the galactic core is also a site of intense star formation. Massive clouds of gas are compressed by the gravity of Sagittarius A*, triggering the birth of new stars. These stars, though short-lived, help to illuminate the otherwise dark and mysterious center of the galaxy. The Milky Way's satellite galaxies, cosmic companions. The Milky Way is not alone in the vastness of space. It is surrounded by a retinue of smaller galaxies, known as satellite galaxies, which orbit the larger spiral like moons around a planet. Some of these satellites are faint and irregular, while others, like the Large and Small Magellanic Clouds, are prominent and easily visible from Earth's southern hemisphere. These satellite galaxies are more than just companions, they are key players in the Milky Way's ongoing evolution. Over the course of billions of years, the Milky Way has absorbed many of its satellite galaxies, incorporating their stars, gas, and dark matter into its own structure. This process of galactic cannibalism is a natural part of the life cycle of galaxies, and it has played a significant role in shaping the Milky Way as we see it today. One of the most striking examples of this process is the Sagittarius dwarf galaxy, a small satellite galaxy that is currently being torn apart by the Milky Way's gravity. The remnants of the Sagittarius dwarf are being stretched into a long, looping stream of stars that wraps around the Milky Way like a cosmic ribbon. Over time, these stars will be fully absorbed into the Milky Way, adding to its mass and altering its structure. Other satellite galaxies, like the Magellanic Clouds, remain relatively intact for now, but they too will eventually be absorbed by the Milky Way. The gravitational interactions between the Milky Way and its satellites can trigger bursts of star formation, as gas clouds are compressed by the tidal forces generated by these encounters. In this way, the Milky Way and its satellites are locked in a complex and dynamic relationship, constantly shaping and reshaping one another over cosmic time scales. The future of the Milky Way, a cosmic merger. Though the Milky Way has existed for billions of years, its story is far from over. In the distant future, the galaxy will undergo one of the most dramatic events in its history, a collision with the Andromeda Galaxy. Andromeda, the Milky Way's nearest large neighbor, is currently about 2.5 million light-years away, but the two galaxies are on a collision course, moving toward each other at a speed of 110 kilometers per second. In approximately 4.5 billion years, the Milky Way and Andromeda will collide, triggering a cosmic event of unparalleled scale. The two galaxies will merge into a single, massive elliptical galaxy, forever changing the structure of both. Although the stars within each galaxy are unlikely to collide due to the vast distances between them, the gravitational interactions will send many stars into new orbits, and the gas clouds within each galaxy will be compressed, triggering new waves of star formation. This galactic merger will also affect the central black holes of both galaxies. The supermassive black holes at the centers of the Milky Way and Andromeda will spiral toward each other, eventually merging into an even larger black hole. This merger will release an enormous amount of energy in the form of gravitational waves, ripples in the fabric of spacetime that were first predicted by Einstein's theory of general relativity. Despite the scale of this event, the merger will unfold over millions of years, and life on any planets within the merging galaxies may not even notice the changes happening on such grand timescales. However, the final result will be a new galaxy, often referred to as Milkomeda, which will be larger and more massive than either of its progenitors. A cosmic perspective, the Milky Way's place in the universe. As we reflect on the Milky Way, it's easy to be awed by the scale and complexity of the galaxy we call home. Yet, even the Milky Way is just one of countless galaxies that fill the universe. Our galaxy is part of the Local Group, a collection of about 50 galaxies, including Andromeda and several smaller galaxies. Beyond the Local Group lies the Virgo supercluster, a massive structure that contains thousands of galaxies, all bound together by the force of gravity. But even the Virgo supercluster is not the largest structure in the universe. Recent observations have revealed that galaxies and galaxy clusters are organized into vast cosmic filaments, forming a web-like structure that spans billions of light-years. This cosmic web is the largest known structure in the universe, and it provides a framework for the distribution of galaxies, dark matter, and gas throughout the cosmos. The Milky Way, like all galaxies, is part of this grand cosmic tapestry, connected to everything else in the universe by the forces of gravity and dark matter. It is a reminder that we are part of something much larger than ourselves, a vast and interconnected universe that has been evolving for billions of years and will continue to evolve for billions more. The galactic dance, stars, planets, and the motion of the Milky Way. One of the most captivating aspects of the Milky Way is the motion that occurs within it. Stars, planets, gas clouds, and dust all move in concert with the gravitational pull of the galaxy's mass, but this movement is far from uniform. The rotation of the Milky Way is a complex dance, driven by both visible and dark matter, creating dynamic motion across a wide range of scales, from the orbit of individual stars to the grand rotation of the entire galaxy around its center. At the most fundamental level, the stars in the Milky Way, including our own Sun, orbit the galactic center in nearly circular paths. This orbital motion is governed by the mass of the galaxy and its distribution, which determines the speed at which stars rotate. Near the center of the galaxy, where the gravitational pull is strongest, stars orbit quickly, while those farther out, in the galactic disk's periphery, rotate more slowly. However, due to the influence of dark matter, even the outer stars rotate faster than would be expected if only visible matter were present. This discovery, made in the 20th century, was one of the first strong pieces of evidence for the existence of dark matter. Our solar system, located about 2/3 of the way from the center of the Milky Way, takes roughly 230 million years to complete one orbit around the galactic center. This journey, known as a galactic year, has seen the Earth and the rest of the planets accompany the Sun through multiple phases of their evolutionary history. To put this in perspective, the last time our solar system was in its current position in the galaxy, dinosaurs roamed the Earth. The constant motion of the solar system through the Milky Way has exposed our planet to varying cosmic environments, including different densities of gas and radiation. But it's not just the stars that move within the galaxy. Entire star clusters and stellar associations, such as open clusters, also drift through the Milky Way. These groups of stars, often formed together from the same gas cloud, move as coherent units, slowly dispersing over time as individual stars are influenced by the gravitational forces of other stars and gas clouds. Some of these star clusters, like the Pleiades, are visible to the naked eye and have been observed by human civilizations for millennia, serving as both navigational aids and cultural symbols. The galactic halo, a realm of ancient stars. Surrounding the Milky Way's disk is the galactic halo, a vast and sparsely populated region that extends far beyond the main body of the galaxy. While the disk is the Milky Way's most visually striking feature, containing the majority of its stars, the halo is equally important for understanding the galaxy's structure and evolution. It is in the halo that some of the oldest stars in the galaxy reside, stars that date back to the earliest stages of the Milky Way's formation, over 13 billion years ago. These ancient stars, often found in globular clusters, provide valuable clues about the early history of the galaxy. Globular clusters are densely packed spheres of stars, containing hundreds of thousands of stars, all orbiting the galaxy's center in highly elliptical orbits. The stars in these clusters are some of the oldest in the universe, with ages that approach the estimated age of the universe itself. Observing these stars allows astronomers to peer back in time, to an era when the Milky Way was still in its infancy, forming from smaller protogalaxies and primordial gas clouds. The halo also contains streams of stars, remnants of smaller galaxies that have been torn apart and assimilated into the Milky Way through the process of galactic cannibalism. These stellar streams are a testament to the galaxy's violent history, revealing the scars of past mergers and collisions. By mapping these streams, astronomers can trace the orbits of stars back to their original galaxies, reconstructing the Milky Way's history as it grew through the accretion of smaller galaxies. While the stars in the halo are fascinating, the dark matter that dominates this region is even more mysterious. Dark matter is believed to form a spherical halo around the galaxy, extending well beyond the visible stars and gas. This halo provides the gravitational pull needed to keep the stars in the outer regions of the galaxy from flying off into space. Though invisible, the presence of dark matter is inferred from the motion of stars and gas within the galaxy, and its influence is a fundamental aspect of the Milky Way's structure. The stellar nursery, star formation in the Milky Way. The Milky Way is a galaxy in constant motion, not only in terms of the orbits of its stars but also in the ongoing process of star formation. Throughout the spiral arms, vast clouds of gas and dust serve as stellar nurseries, where new stars are born. These regions, known as molecular clouds, are dense areas where gas, mostly hydrogen, begins to collapse under its own gravity. As the gas compresses, it heats up, eventually igniting nuclear fusion in the core of the forming star. One of the most famous star-forming regions in the Milky Way is the Orion Nebula, a bright and active nursery located about 1,300 light-years from Earth. Visible to the naked eye, the Orion Nebula is home to hundreds of young stars, many of which are still in the process of forming. Some of these stars are surrounded by protoplanetary disks, rotating disks of gas and dust that may eventually form planets, moons, and other objects. In this way, the process of star formation is closely linked to the formation of planetary systems, including those that could potentially harbor life. The star-forming regions of the Milky Way are not evenly distributed but are concentrated in the spiral arms, where the density of gas is highest. As the galaxy rotates, shock waves from supernovae interactions with spiral density waves trigger the collapse of gas clouds, initiating the star formation process. These bursts of star formation are not isolated events but are part of a larger cycle in which stars form, live out their lives, and eventually die, returning their material to the interstellar medium to fuel the next generation of stars. Massive stars, those much larger than the Sun, play a particularly important role in this cycle. These stars burn through their fuel quickly, often in just a few million years, before exploding as supernovae. The supernovae not only enrich the surrounding gas with heavy elements but also send shock waves through the galaxy, triggering the collapse of nearby gas clouds and promoting the formation of new stars. In this way, the death of one generation of stars directly contributes to the birth of the next, ensuring that the cycle of cosmic creation and destruction continues. The cosmic web, the Milky Way's place in the universe. While the Milky Way is a vast and complex structure, it is but a single galaxy in the larger cosmic web, a vast network of galaxies, dark matter, and intergalactic gas that stretches across the universe. This cosmic web is the largest known structure in the universe, composed of galaxy clusters, superclusters, and immense voids, all connected by filaments of dark matter and gas. The Milky Way is part of the Local Group, a small collection of galaxies that includes Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. Together, these galaxies are gravitationally bound, moving through space as a cohesive unit. Beyond the Local Group lies the Virgo supercluster, a much larger structure that contains thousands of galaxies, all bound together by their mutual gravitational attraction. The Local Group is located near the edge of the Virgo supercluster, which in turn is part of an even larger structure known as Laniakea, a supercluster that contains hundreds of thousands of galaxies spread across 500 million light-years. These superclusters form the nodes of the cosmic web, connected by long filaments of galaxies and dark matter, with vast empty spaces, or voids, in between. The discovery of the cosmic web has revolutionized our understanding of the universe. It reveals that galaxies are not randomly distributed but are instead organized into vast structures that stretch across the cosmos. The Milky Way, like all galaxies, is part of this larger cosmic structure, connected to everything else in the universe by the invisible force of gravity. These structures are not static but are constantly evolving, shaped by the expansion of the universe and the interactions between galaxies and dark matter. As we continue to explore the universe, the Milky Way remains a focal point of our curiosity and wonder. It is our home, a place of unimaginable beauty and complexity, and yet it is also just one small part of a much larger cosmic story. From the birth of stars to the motion of galaxies, from the mysteries of dark matter to the grand scale of the cosmic web, the Milky Way reminds us that we are part of something far greater than ourselves, a universe filled with wonder, mystery, and endless possibilities. The galactic ecosystem, a balanced cycle of creation and destruction. The Milky Way, like any galaxy, operates as a complex ecosystem, where the life cycles of stars and the interactions of gas, dust, and dark matter maintain a delicate balance of creation and destruction. This cycle of birth, evolution, and death plays out over billions of years, shaping the evolution of the galaxy and determining the conditions for future star formation and planetary development. At the heart of this cycle are the molecular clouds, the cold, dense regions of gas where new stars are born. These clouds, composed primarily of hydrogen molecules, are often hundreds of light-years across and can contain enough material to form thousands of stars. As gravity slowly pulls the gas together, the densest regions collapse, forming protostars. The intense pressure and heat in the core of these protostars eventually ignite nuclear fusion, marking the birth of a new star. The process of star formation is not uniform. In some regions of the galaxy, star formation occurs at a rapid pace, while in others, it proceeds more slowly or has ceased altogether. This variation is influenced by factors such as the availability of gas, the presence of supernovae or other energetic events, and the density waves that propagate through the spiral arms. The Milky Way's spiral arms are rich in gas and dust, making them prime locations for star formation. However, as the galaxy ages and the gas is used up, the rate of star formation will gradually decline. When stars exhaust their nuclear fuel, they enter the final stages of their life cycles. For stars like the Sun, this means expanding into red giants before shedding their outer layers, leaving behind a white dwarf, a dense remnant of the star's core. For more massive stars, the end comes in the form of a supernova explosion. These powerful blasts not only disperse the heavy elements produced in the star's core but also release enormous amounts of energy that can trigger the formation of new stars in nearby gas clouds. Supernovae are among the most violent events in the galaxy, but they are also essential to its continued evolution. Without the heavy elements produced in these stellar explosions, planets like Earth could not form, and the complex chemistry needed for life would not exist. The material ejected by supernovae enriches the interstellar medium, providing the raw ingredients for future generations of stars and planets. In this way, the death of one generation of stars lays the foundation for the next, ensuring that the Milky Way remains a vibrant, evolving system. The Milky Way's stellar population, giants, dwarfs, and everything in between. The Milky Way is home to a vast array of stars, spanning a wide range of sizes, temperatures, and lifetimes. From the smallest, dimmest red dwarfs to the most massive and luminous blue giants, these stars represent the full diversity of stellar evolution. Each type of star plays a unique role in the galaxy, contributing to its overall structure and dynamics. Red dwarfs are by far the most common type of star in the Milky Way, accounting for about 70% of all stars. These small, cool stars burn their fuel very slowly, allowing them to live for trillions of years, far longer than the current age of the universe. Despite their abundance, red dwarfs are difficult to observe because of their low luminosity. However, their longevity and stability make them important for the study of planetary formation and the potential for life. Many of the exoplanets discovered in recent years orbit red dwarfs, raising the possibility that these stars could host habitable worlds. At the opposite end of the spectrum are the massive blue giants. These stars are rare but incredibly bright, shining thousands or even millions of times more brightly than the sun. Blue giants burn through their nuclear fuel at an astonishing rate, living for only a few million years before exploding as supernovae. Despite their short lifespans, blue giants have a significant impact on their surroundings, producing strong stellar winds that shape the interstellar medium and influencing the formation of new stars. In between these extremes are stars like the Sun, known as yellow dwarfs. These stars are relatively stable, burning hydrogen in their cores for billions of years before evolving into red giants. The Sun, now about halfway through its life, will eventually expand into a red giant, consuming the inner planets, including Earth, before shedding its outer layers and leaving behind a white dwarf. White dwarfs are the remnants of stars that were once similar to the Sun. These dense, compact objects are no longer capable of nuclear fusion, but they continue to radiate heat for billions of years as they slowly cool. Over time, white dwarfs will fade into black dwarfs, cold, dead remnants that no longer emit light. However, this process takes longer than the current age of the universe, so no black dwarfs are thought to exist yet. The diversity of stellar types in the Milky Way reflects the galaxy's ongoing process of star formation and evolution. Each generation of stars contributes to the overall composition of the galaxy, enriching the interstellar medium with heavy elements and shaping the galactic environment in which new stars and planets form. The Milky Way's satellite galaxies, cosmic neighbors. While the Milky Way is a massive and complex structure in its own right, it is not an isolated entity. Surrounding the Milky Way are dozens of smaller satellite galaxies that orbit the larger galaxy, interacting with it gravitationally and occasionally merging with it. These satellite galaxies are important for understanding the Milky Way's evolution, as they provide fresh material for star formation and influence the galaxy's overall structure. Among the most prominent of these satellite galaxies are the Large and Small Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere. These galaxies are currently interacting with the Milky Way, with gas and stars being pulled from them by the larger galaxy's gravitational forces. Over time, these interactions may lead to the eventual merger of the Magellanic Clouds with the Milky Way, adding to its mass and altering its structure. The Milky Way has already absorbed several smaller galaxies in the past. Evidence of these mergers can be seen in the form of stellar streams, long, thin trails of stars that stretch across the sky, marking the remnants of once independent galaxies that have been torn apart by the Milky Way's gravity. These streams provide a glimpse into the Milky Way's dynamic history, showing that galaxies are not static structures but are constantly evolving through interactions with their neighbors. In addition to the Magellanic Clouds, the Milky Way is orbited by several other dwarf galaxies, including the Sagittarius Dwarf Galaxy, which is currently being torn apart and absorbed by the Milky Way. These dwarf galaxies are much smaller than the Milky Way, containing only a fraction of its stars, but their interactions with the larger galaxy play a key role in shaping its future. As the Milky Way continues to grow through mergers with these smaller galaxies, its mass increases, and its spiral structure may become more pronounced. The galactic future, a collision with Andromeda. The Milky Way's future is set to be even more dramatic than its past. In approximately 4.5 billion years, the Milky Way will collide with the Andromeda Galaxy, its nearest large neighbor. Andromeda, currently located about 2.5 million light-years away, is on a collision course with the Milky Way, driven by the mutual gravitational pull between the two galaxies. This cosmic event, known as a galactic merger, will be one of the most significant events in the Milky Way's history. As the two galaxies approach each other, their outer edges will begin to interact, pulling gas and stars out of both galaxies and creating long tidal tails. Eventually, the galaxies will collide, their stars passing by one another without direct collisions due to the vast distances between them. However, the gravitational forces will cause dramatic changes in the structure of both galaxies. The collision will trigger intense bursts of star formation as gas clouds are compressed by the gravitational interactions. Some stars may be flung out of the galaxies entirely, while others will settle into new orbits. Over the course of several billion years, the two galaxies will merge into a single, larger elliptical galaxy. The spiral arms of both galaxies will be disrupted, and the resulting galaxy will bear little resemblance to the Milky Way or Andromeda as we know them today. At the center of this new galaxy, the supermassive black holes of both the Milky Way and Andromeda will merge, creating an even more massive black hole. This merger will release an enormous amount of energy in the form of gravitational waves, rippling through the fabric of spacetime. Despite the scale of the event, the merger will unfold over millions of years, and life on any planets in the merging galaxies may continue largely unaffected. A cosmic reflection, our place in the Milky Way. As we contemplate the future of the Milky Way and its place in the larger universe, we are reminded of our own place within this grand cosmic structure. Our Sun, one of hundreds of billions of stars in the galaxy, orbits quietly in the galactic suburbs, far from the chaotic center but still very much a part of the dynamic life of the galaxy. The planets, including Earth, formed from the same material as the stars, shaped by the same forces that govern the entire galaxy. The Milky Way is more than just a collection of stars, gas, and dust. It is a living, evolving system, constantly changing as stars are born and die, galaxies merge, and dark matter exerts its invisible influence. It is our home, a place of incredible beauty and complexity, and yet it is just one of countless galaxies that fill the universe. As we look to the future, both for the Milky Way and for humanity, we are left with a profound sense of wonder. The galaxy's future is tied to the larger cosmic story of the universe itself, from the distant past when the first galaxies formed to the far future when the Milky Way will merge with Andromeda and eventually settle into a new, larger structure. Through it all, the galaxy will continue to evolve, a testament to the power of cosmic forces and the enduring mystery of the universe. Galactic recycling, the interstellar medium and the cycle of matter. The Milky Way is not just a galaxy of stars, it is also home to an enormous amount of interstellar matter, gas, dust, and other particles that fill the space between stars. This interstellar medium, ISM, is the raw material from which stars and planets form, and it plays a crucial role in the life cycle of the galaxy. The ISM is both a nursery for new stars and a graveyard for the remnants of old ones, as stars continuously return material to this vast reservoir over the course of their lives. The interstellar medium is primarily composed of hydrogen, the simplest and most abundant element in the universe. However, it also contains traces of heavier elements, carbon, oxygen, nitrogen, and more, created inside stars and ejected into space during supernova explosions or the later stages of stellar evolution. These elements are crucial for the formation of planets, moons, and the complex chemistry that leads to the possibility of life. In the denser regions of the ISM, vast molecular clouds exist, where gas is cool enough to form molecules such as hydrogen, H2, carbon monoxide, CO, and even organic molecules like methanol. These molecular clouds are the birthplaces of stars. Under the force of gravity, the gas in these clouds begins to collapse, forming clumps that eventually ignite as new stars. This process of stellar birth is accompanied by the formation of protoplanetary disks, which may give rise to planetary systems like our own. The ISM is not static, it is constantly being enriched and altered by the life cycles of stars. When a star dies, it often returns much of its material back to the interstellar medium. For low and medium-mass stars like the Sun, this process occurs as the star sheds its outer layers to form a planetary nebula, leaving behind a white dwarf. For more massive stars, this recycling is much more dramatic, as the star explodes in a supernova, spewing heavy elements across vast distances. These heavy elements, sometimes referred to as metals by astronomers, include the building blocks of planets and, ultimately, life. Through this constant recycling of material, the Milky Way maintains a dynamic equilibrium. As new stars form, they use up gas from the ISM, but at the same time, dying stars return material, enriching the galaxy with the elements needed to fuel the next generation of stars. This cycle has been ongoing for billions of years and will continue long into the future, gradually shaping the composition and evolution of the galaxy. The galactic halo and stellar archaeology. The halo of the Milky Way, while far less dense than the disk, holds significant importance in understanding the early history of the galaxy. This nearly spherical region, extending far beyond the visible disk, contains some of the oldest stars in the Milky Way. These ancient stars, often found in globular clusters, are key to understanding the early formation processes of our galaxy. Globular clusters are tight, gravitationally bound groups of stars that may contain hundreds of thousands of stars, all born at nearly the same time. The stars in these clusters are much older than the Sun, often more than 10 billion years old, making them some of the oldest objects in the galaxy. By studying the light from these stars, astronomers can deduce their chemical compositions and ages, providing valuable insights into the conditions that existed when the Milky Way was just forming. The galactic halo is also home to stellar streams, long, thin trails of stars that stretch across the sky. These streams are the remnants of dwarf galaxies and star clusters that were gravitationally disrupted and absorbed by the Milky Way. By mapping the orbits of these stars, astronomers can trace their origins and reconstruct the history of past mergers between the Milky Way and smaller galaxies. This process of galactic cannibalism, where larger galaxies absorb smaller ones, has been a key driver of the Milky Way's growth over billions of years. The halo is dominated by dark matter, which extends far beyond the visible stars and gas. This dark matter halo provides the gravitational pull that keeps the galaxy together, particularly in the outer regions where the visible matter alone would be insufficient to prevent stars from escaping into intergalactic space. Understanding the distribution and nature of dark matter in the halo is one of the most important challenges in modern astrophysics, as it holds the key to unlocking the full picture of how galaxies like the Milky Way form and evolve. Galactic dynamics, the rotational puzzle. One of the most intriguing aspects of the Milky Way is the way it rotates. Early observations of the galaxy's stars revealed a surprising inconsistency. Stars in the outer regions of the galaxy orbit the galactic center much faster than expected. According to the laws of Newtonian mechanics, stars farther from the center, where the mass of the galaxy should be thinner, should move more slowly. Instead, they maintain nearly the same speed as stars closer to the center, defying expectations. This puzzling behavior led astronomers to the discovery of dark matter, an invisible substance that does not interact with light but exerts a significant gravitational pull. Dark matter is thought to make up about 85% of the matter in the universe and forms a halo around galaxies, including the Milky Way. This dark matter provides the additional gravitational force needed to explain the high orbital speeds of stars in the galaxy's outer regions. Without dark matter, the stars at the edges of the Milky Way would fly off into space. Its presence binds the galaxy together and ensures its rotation remains stable. However, the true nature of dark matter remains one of the greatest mysteries of modern science. Despite extensive research, no direct detection of dark matter has yet been achieved, and its exact composition is still unknown. Understanding dark matter is crucial not just for understanding the Milky Way but for piecing together the entire cosmic puzzle. The quest for extraterrestrial life in the Milky Way. One of the most profound questions humanity has ever asked is whether we are alone in the universe. The Milky Way, with its billions of stars and even more planets, presents an enormous laboratory for this quest. The discovery of exoplanets, planets orbiting stars other than the Sun, has transformed our understanding of planetary systems and raised the tantalizing possibility that life could exist elsewhere in our galaxy. To date, thousands of exoplanets have been discovered, many of them in the so-called habitable zone, where conditions might be just right for liquid water to exist on a planet's surface, a key ingredient for life as we know it. Some of these planets are Earth-sized, orbiting stars that are stable over long periods of time, raising the possibility that life could have developed and thrived in such environments. The search for extraterrestrial life extends beyond just finding planets that could support life. Projects like SETI, Search for Extraterrestrial Intelligence, have been scanning the skies for decades, listening for radio signals or other signs of advanced civilizations. While no definitive signal has yet been detected, the sheer number of stars in the Milky Way, combined with the diversity of planetary systems, suggests that the search is far from over. One of the most exciting developments in this field is the study of extremophiles, microorganisms on Earth that can survive in extreme environments, such as deep ocean vents or acidic hot springs. These organisms show that life can thrive in conditions that were once thought to be inhospitable. This has led scientists to expand the definition of where life might exist in the galaxy, including moons like Europa or Enceladus, which have subsurface oceans beneath their icy crusts, and Mars, where evidence of ancient water has been found. The discovery of even microbial life elsewhere in the Milky Way would have profound implications for our understanding of biology, evolution, and our place in the universe. It would suggest that life is not unique to Earth but is a common outcome of the right environmental conditions, a cosmic phenomenon rather than a planetary anomaly. The Milky Way's interaction with Andromeda, a future collision. As majestic as the Milky Way is today, its future is already written in the stars, literally. The Milky Way and its neighbor, the Andromeda Galaxy, are on a slow-motion collision course. Andromeda, currently about 2.5 million light-years away, is the largest galaxy in the local group and is moving toward the Milky Way at a speed of roughly 110 kilometers per second. In approximately 4.5 billion years, the two galaxies will collide and merge, creating a new, larger galaxy. This cosmic collision will be a gradual process, unfolding over hundreds of millions of years. When the two galaxies meet, their outer regions will interact first, and stars from both galaxies will be thrown into new orbits. Despite the dramatic nature of this event, direct collisions between individual stars are unlikely due to the vast distances between them. Instead, the gravitational forces of the merging galaxies will cause stars to shift and the gas within both galaxies to compress, triggering intense bursts of star formation. Eventually, the Milky Way and Andromeda will settle into a new, elliptical-shaped galaxy, often referred to as Milkomeda. This new galaxy will be larger and more massive than either of its progenitors, and its central supermassive black holes will merge into an even larger black hole, releasing energy in the form of gravitational waves. Though the collision will dramatically alter the structure of both galaxies, it is not something that will have an immediate impact on life within the Milky Way. By the time this event occurs, the Sun will have already evolved into a red giant and left behind a white dwarf. Any surviving planets may not even notice the changes in the night sky as the merger unfolds over such vast timescales. The grand perspective, the Milky Way in the cosmic web. As we look at the Milky Way, we are reminded that our galaxy, grand and complex as it is only one small part of an even larger cosmic structure, the universe's vast and intricate web. Galaxies are not isolated islands of stars but are instead interconnected in a cosmic web of dark matter, gas, and other galaxies. This web is the scaffolding of the universe, stretching across billions of light-years, binding galaxies into clusters and superclusters, and weaving through immense voids where few, if any, galaxies reside. The Milky Way is part of the Local Group, a collection of around 50 galaxies, including Andromeda and several smaller satellite galaxies like the Magellanic Clouds. The Local Group is, in turn, part of the Virgo supercluster, a massive concentration of thousands of galaxies that extends across hundreds of millions of light-years. The Virgo supercluster is just one part of an even larger structure, known as Laniakea, a supercluster of galaxies that encompasses hundreds of thousands of galaxies spread over an immense volume of space. The discovery of this cosmic web has revolutionized our understanding of the universe. It has shown that galaxies are not randomly distributed but are instead organized into massive, interconnected structures that stretch across the cosmos. These structures are shaped by the gravitational influence of dark matter, which forms the invisible backbone of the universe. Without dark matter, the cosmic web would not exist, and galaxies would be distributed more randomly. The Milky Way, along with every other galaxy, is moving within this web, influenced by the gravitational pull of its neighbors and the dark matter that permeates the universe. These motions are not random but follow the contours of the cosmic web, with galaxies flowing along the filaments and toward the dense nodes of superclusters. This dynamic movement is a testament to the interconnectedness of the universe, where nothing exists in isolation, and everything is part of a larger, grander whole. The Galactic Past, tracing the Milky Way's origins. Understanding the Milky Way today requires us to look back in time, to the earliest days of the universe, when galaxies were just beginning to form. The Milky Way, like all galaxies, was born in the aftermath of the Big Bang, around 13.8 billion years ago. In the first few 100 million years after the Big Bang, the universe was a hot, dense sea of hydrogen and helium, with no stars or galaxies. But as the universe expanded and cooled, tiny fluctuations in the density of matter began to grow, eventually leading to the formation of the first stars and galaxies. The Milky Way began as a small protogalaxy, a collection of stars, gas, and dark matter that gradually grew in size through mergers with other protogalaxies. Over the next several billion years, these mergers continued, with the Milky Way absorbing smaller galaxies and growing into the large spiral galaxy we see today. This process of galactic mergers is still ongoing, as evidenced by the streams of stars in the galactic halo, which are the remnants of past collisions with smaller galaxies. The early Milky Way was a much more chaotic place than it is today. The galaxy was smaller, with less well-defined spiral arms, and star formation occurred at a much faster rate. Over time, as the galaxy grew and settled into its current form, the rate of star formation slowed, and the galaxy took on its familiar spiral structure, with the Sun forming about 4.6 billion years ago in one of the quieter regions of the galactic disk. By studying the oldest stars in the galaxy, astronomers can trace the history of the Milky Way back to these early days. The composition of these ancient stars provides clues about the conditions that existed when the galaxy was young, and their distribution in the halo and bulge helps to map out the galaxy's early mergers and growth. These stars are like fossils, preserving the history of the galaxy's formation and evolution. The galactic future, the end of star formation. As the Milky Way continues to evolve, one of the most significant changes in its future will be the gradual decline of star formation. While new stars are still forming in the galaxy today, the rate of star formation has been steadily decreasing over the past few billion years. This decline is driven by the depletion of the gas reservoirs that fuel star formation. As stars form, they use up the available gas, and although some gas is returned to the interstellar medium when stars die, much of it is lost to the galaxy, expelled into intergalactic space by supernovae and stellar winds. Eventually, the Milky Way will run out of the gas needed to form new stars. When this happens, the galaxy will enter a quiescent phase, where no new stars are born, and the existing stars slowly burn out and die. The galaxy will become a much darker, quieter place, with only dim red dwarf stars and cooling white dwarfs remaining. This fate awaits all galaxies, as the universe continues to expand and the gas needed for star formation becomes increasingly scarce. The collision with Andromeda will temporarily reignite star formation in the Milky Way, as the gas from both galaxies is compressed and new stars are born in the aftermath of the merger. However, this burst of star formation will be short-lived on cosmic timescales, and the resulting elliptical galaxy will eventually run out of gas as well, becoming a quiescent, slowly fading structure. A cosmic perspective, life in the Milky Way. The Milky Way, with its billions of stars and even more planets, is a galaxy rich with potential for life. The discovery of thousands of exoplanets in recent years has opened up new possibilities for understanding the diversity of planetary systems and the conditions under which life might arise. While Earth is the only known planet to harbor life, the sheer number of planets in the Milky Way suggests that life could be more common than we once thought. One of the most exciting developments in the search for life is the study of habitable zones, the regions around stars where conditions might be right for liquid water to exist. Planets in these zones, especially those that are Earth-sized, are prime candidates for the search for extraterrestrial life. While many of these planets orbit stars much smaller and cooler than the Sun, such as red dwarfs, the discovery of these potentially habitable worlds has expanded our understanding of where life might exist. The search for life in the Milky Way also extends beyond planets. Some of the moons in our own solar system, such as Europa and Enceladus, have subsurface oceans that could harbor life beneath their icy crusts. These moons may provide clues about the potential for life in similar environments around other stars, where icy moons orbit gas giants. The possibility of life elsewhere in the Milky Way raises profound questions about our place in the universe. If life is common in the galaxy, what does that mean for humanity's significance? And if we are alone, what does that say about the uniqueness of Earth and the delicate conditions that allowed life to thrive here? These questions drive the ongoing search for life and the exploration of distant planets, as we seek to understand not only the Milky Way but our own role within it. The Endless Journey, humanity's exploration of the Milky Way. As we look toward the future, humanity's relationship with the Milky Way is evolving. For thousands of years, we have gazed at the stars and wondered about the nature of the galaxy. Today, we are on the cusp of a new era of exploration, with the potential to reach beyond the confines of our solar system and explore the galaxy itself. Robotic probes, such as NASA's Voyager spacecraft, have already begun the journey beyond the boundaries of the solar system, traveling into the interstellar medium. These spacecraft, though limited by the speed of current technology, represent humanity's first steps into the wider galaxy. In the future, new technologies may allow us to explore the stars more directly, sending probes to nearby exoplanets or even establishing colonies on other worlds. The challenges of interstellar travel are immense, but the potential rewards are equally vast. Exploring the Milky Way could provide answers to some of the most fundamental questions about the nature of the universe and the origins of life. It could also offer new opportunities for the survival of humanity, as we seek to ensure our long-term future in a galaxy that is constantly evolving. As we embark on this journey, we are reminded that the Milky Way is not just a distant collection of stars, it is our home. It is the place where humanity was born, where we have lived out our history, and where we continue to explore and dream. The galaxy's vastness is humbling, but it also inspires us to reach beyond our small corner of the cosmos, to seek out new horizons and new possibilities in the great, unfolding story of the universe. The Milky Way, a journey without end. In contemplating the Milky Way, we are drawn into a story that spans billions of years, from the galaxy's formation in the aftermath of the Big Bang to its future collision with Andromeda and beyond. It is a story of creation and destruction, of stars and planets, of life and the search for meaning in a vast, ever-changing cosmos. As we look up at the night sky, we are reminded that we are part of something far greater than ourselves. The stars that shine down on us are not just distant points of light, they are the building blocks of galaxies, the creators of planets, and the seeds of life. The Milky Way is our home, a place of wonder and mystery, and yet it is also a single chapter in the much larger story of the universe. Our journey through the Milky Way is ongoing, an adventure that stretches across time and space. Whether we are exploring the galaxy's distant past, pondering its future, or seeking out new worlds, we are part of a cosmic narrative that has no end. The Milky Way is a reminder of the beauty and complexity of the universe, and of the endless possibilities that await us as we continue our quest to understand our place in the cosmos. The cosmic tapestry, the Milky Way's role in the universe's evolution. The Milky Way is just one piece in a vast cosmic tapestry, a universe that has been evolving since the dawn of time. Our galaxy's formation and growth have been influenced by the larger universe, shaped by forces that extend beyond its boundaries. As the universe expanded after the Big Bang, galaxies like the Milky Way coalesced, pulled together by gravity, and began their long journey through space and time. But the story of the Milky Way is intertwined with the broader evolution of the universe itself, a narrative that stretches from the first moments of creation to the present day and far into the future. One of the most profound discoveries of the last century was that the universe is expanding. The galaxies we see around us are moving away from one another, carried by the expansion of space itself. This expansion, first discovered by Edwin Hubble, showed that the universe had a beginning, a moment in time when all matter, energy, and space were compressed into a singular point. From this moment, the universe began to expand and cool, allowing galaxies, stars, and eventually planets to form. The Milky Way, like all galaxies, formed from the primordial hydrogen and helium that filled the early universe. Over billions of years, this gas clumped together under the force of gravity, forming stars and galaxies. The earliest stars in the Milky Way were massive and short-lived, and their supernova explosions enriched the galaxy with heavy elements, carbon, oxygen, and iron, that would later form planets like Earth. These elements, created in the hearts of dying stars, are the building blocks of life and have been distributed throughout the galaxy, seeding future generations of stars and planets. As the universe continues to expand, the Milky Way's relationship with its cosmic neighbors will change. The universe's expansion is accelerating, driven by a mysterious force known as dark energy. This acceleration will eventually cause galaxies to move so far apart that they will no longer be visible to one another. Over time, the Milky Way and its nearby galaxies will become increasingly isolated, cut off from the rest of the universe by the vast, empty voids of space. In this distant future, the Milky Way will exist as a solitary structure, its stars gradually burning out as the universe grows colder and darker. The search for understanding, humanity's quest to know the galaxy. The Milky Way has always been a source of wonder and fascination for humanity. From the earliest civilizations to modern astronomers, people have gazed up at the stars, seeking to understand the nature of the galaxy and their place within it. Ancient cultures saw the Milky Way as a celestial river, a pathway for souls, or the spine of the night sky. Its luminous band, stretching across the heavens, has inspired myths, stories, and scientific inquiry for millennia. Today, our understanding of the Milky Way is built on centuries of observation and exploration. From early telescopes to modern space missions, we have gradually pieced together the structure and composition of our galaxy. Astronomers have mapped its spiral arms, studied its star clusters, and uncovered the hidden mass of dark matter that holds it together. Yet, despite all we have learned, the Milky Way still holds many mysteries, and our quest for knowledge continues. One of the most significant advances in our understanding of the Milky Way came with the development of radio astronomy. By observing the galaxy in radio waves, astronomers were able to peer through the dust that obscures much of the visible light from the galactic center. This allowed them to map the spiral arms in greater detail and discover the supermassive black hole, Sagittarius A*, lurking at the heart of the Milky Way. Radio astronomy also revealed the presence of vast clouds of gas and dust, where new stars are being born, and helped to trace the motion of stars and gas throughout the galaxy. Space-based observatories, such as the Hubble Space Telescope, have also played a crucial role in expanding our knowledge of the Milky Way. By observing the galaxy from above the Earth's atmosphere, these telescopes have provided stunning images of star-forming regions, planetary nebulae, and distant galaxies. They have also helped to measure the distance to other galaxies, refining our understanding of the Milky Way's position in the cosmic web. But perhaps the most exciting advances in recent years have come from the discovery of exoplanets. With the help of space missions like Kepler and TESS, astronomers have identified thousands of planets orbiting other stars in the Milky Way. Some of these planets are located in the habitable zones of their stars, where conditions might be right for life to exist. The discovery of these distant worlds has transformed our understanding of the galaxy, showing that planetary systems are common and raising the possibility that life could exist elsewhere in the Milky Way. The ethical questions of galactic exploration. As humanity embarks on its journey to explore the Milky Way, we are confronted with profound ethical questions. The expansion of human presence beyond Earth, whether through robotic exploration or future human colonization of other planets, raises important issues about our responsibilities as stewards of the galaxy. How should we interact with other worlds, and what obligations do we have to protect the environments and potential life forms we may encounter? One of the most immediate ethical concerns is the potential for contamination. As we explore planets, moons, and other celestial bodies in the Milky Way, there is a risk that we could introduce Earth-based microbes or other forms of life that could disrupt the ecosystems of these worlds. Planetary protection protocols, designed to prevent such contamination, are in place to safeguard both the environments we explore and the scientific integrity of our search for extraterrestrial life. These protocols ensure that missions to places like Mars or the icy moons of the outer solar system are carefully planned and executed to minimize the risk of contamination. But beyond contamination, there are broader questions about our role in the galaxy. If we discover life on other worlds, whether microbial or intelligent, how should we interact with it? Should we attempt to communicate with intelligent civilizations, and if so, what message should we send? The possibility of contact with extraterrestrial life raises deep philosophical and ethical questions about our place in the cosmos and our responsibilities as a species. Even in the absence of other life forms, the ethical implications of human expansion into the galaxy are significant. The colonization of other planets, for example, may offer a solution to the long-term survival of humanity, but it also raises questions about the environmental and cultural impacts of such endeavors. As we expand our reach into the Milky Way, we must consider how to balance the pursuit of knowledge and survival with the preservation of the galaxy's natural beauty and potential diversity of life. The Milky Way's legacy, a reflection on time and eternity. As we contemplate the future of the Milky Way, we are reminded that galaxies, like all things in the universe, are not eternal. Stars are born and die, gas is used up, and even galaxies themselves are destined to change and evolve. In the distant future, the Milky Way will no longer exist in its current form. Its stars will have burned out, its gas will be gone, and its spiral arms will have merged with those of Andromeda in the cosmic ballet of galactic mergers. Yet, the legacy of the Milky Way will endure. The stars that shine in our night sky are a testament to billions of years of cosmic evolution, and the planets that orbit those stars are the product of the galaxy's long and complex history. Even after the galaxy has merged with Andromeda and its spiral arms have disappeared, the stars and planets that formed within the Milky Way will continue to orbit the center of the new, larger galaxy. The Milky Way's story is, in many ways, the story of the universe itself. It is a microcosm of the processes that govern the cosmos: gravity, star formation, galactic evolution, and the interplay of matter and dark matter. As we study the Milky Way, we gain insight into the forces that have shaped not only our galaxy but the entire universe. In reflecting on the Milky Way, we are also reminded of the ephemeral nature of time. The galaxy has existed for billions of years and will continue to evolve for billions more. Our own lives, by comparison, are fleeting, a mere blink in the vast timeline of the cosmos. Yet, despite our brief existence, we are connected to the stars and the galaxies. The atoms in our bodies were forged in the hearts of dying stars, and the same forces that govern the motions of the planets shape the structure of the Milky Way. In contemplating the Milky Way, we are faced with both the immensity of the universe and the intimate connections that bind us to it. We are made of the same material as the stars, and we are part of the same cosmic story. The galaxy is not just a distant collection of stars, it is our home, our origin, and our future. As we continue to explore and understand the Milky Way, we are reminded of the endless possibilities that await us in the universe, and of the profound mystery that lies at the heart of existence. A journey of exploration without end. The Milky Way is a galaxy of wonders, mysteries, and endless possibilities. It is a place where stars are born and die, where planets form and evolve, and where life may one day be discovered beyond the confines of Earth. It is a galaxy that stretches across 100,000 light-years, containing hundreds of billions of stars and even more planets, each with its own story to tell. As we continue our journey of exploration, we are reminded that the Milky Way is not just a distant object in the sky, it is our cosmic neighborhood, a place of beauty and complexity, and the home of all life as we know it. The quest to understand the galaxy is a journey without end, as each discovery leads to new questions and deeper insights. In the vast expanse of the universe, the Milky Way is but one galaxy among billions, yet it holds a special significance for us. It is the galaxy that gave birth to the Sun, to Earth, and to the human species. It is a place of infinite wonder, where the laws of physics, the forces of nature, and the mysteries of existence come together in a grand cosmic dance. As we look up at the stars, we are reminded that we are part of this galaxy, part of the universe, and part of a story that has been unfolding for billions of years and will continue for billions more. The Milky Way is our home, our inspiration, and our guide as we explore the cosmos, seeking to understand the mysteries of the universe and our place within it. The cosmic connection, life and the Milky Way's role in universal evolution. The Milky Way, with all its stars, planets, and cosmic structures, serves as a grand stage for one of the universe's greatest mysteries, the origin and evolution of life. While Earth is currently the only known planet to host life, the sheer number of stars and planets within the Milky Way raises the tantalizing possibility that life could exist elsewhere in the galaxy. If life is found beyond Earth, it would not only transform our understanding of biology but also link our existence to a broader cosmic narrative, one that spans across time, space, and the very fabric of the universe. The question of whether life exists elsewhere in the Milky Way is deeply tied to the galaxy's ability to foster the conditions necessary for its emergence. Life as we know it depends on several key ingredients: water, carbon-based molecules, and energy sources like sunlight or chemical reactions. The Milky Way, with its billions of stars and even more planets, provides a vast array of environments where these conditions might be met. The search for habitable worlds, therefore, extends far beyond our solar system, into the dense star clusters and spiral arms of the galaxy, where countless other planets orbit their stars in a variety of conditions. The discovery of exoplanets has been a game-changer in this quest. In recent years, astronomers have discovered thousands of planets orbiting stars throughout the Milky Way, many of which reside in their star's habitable zone, where liquid water could potentially exist. Some of these planets are rocky, like Earth, and have atmospheres that might be capable of supporting life. The diversity of planetary systems in the Milky Way suggests that the galaxy is teeming with potential, waiting to be explored and understood. Beyond planets, there are other intriguing possibilities for life in the Milky Way. Moons like Europa and Enceladus, which orbit Jupiter and Saturn, have subsurface oceans hidden beneath their icy crusts. These moons are believed to harbor environments that could support microbial life, sustained by geothermal energy from their planet's tidal forces. If life exists in these hidden oceans, it would suggest that life can arise in places far beyond the familiar environments of Earth-like planets, opening up new avenues of exploration across the galaxy. The evolution of intelligence in the Milky Way. While the search for microbial life is an exciting prospect, the discovery of intelligent life would have even more profound implications for our understanding of the Milky Way and our place within it. The development of intelligence, defined as the ability to reason, communicate, and manipulate the environment, has occurred on Earth through billions of years of evolution, but could it have also arisen elsewhere in the galaxy? Intelligent life may be extremely rare, or it could be far more common than we currently realize. The vast distances between stars and the relatively short time scales on which intelligent civilizations might exist make detecting other advanced civilizations a formidable challenge. However, the possibility of making contact with intelligent beings in the Milky Way has inspired projects like the Search for Extraterrestrial Intelligence, SETI, which listens for radio signals or other forms of communication from distant civilizations. The famous Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of intelligent civilizations that might exist in the Milky Way. The equation takes into account factors such as the number of stars in the galaxy, the fraction of those stars with planets, the number of planets that could support life, and the likelihood of life developing intelligence. While many of these variables are still unknown, the rapid pace of exoplanet discovery is helping to refine our estimates and bring us closer to answering the age-old question: are we alone in the galaxy? If intelligent life does exist elsewhere in the Milky Way, what would it mean for humanity? The discovery of another intelligent species would force us to rethink our place in the universe, just as earlier discoveries, such as the heliocentric model of the solar system, challenged our view of ourselves as the center of creation. The realization that we are part of a broader community of intelligent beings, spread across the galaxy, would have profound implications for philosophy, religion, and ethics. Galactic civilizations, the future of humanity in the Milky Way. As humanity continues to explore the Milky Way, one of the most compelling questions is whether we will one day become a galactic civilization. The idea of humans spreading beyond Earth to colonize other planets, moons, and even distant star systems has long been a staple of science fiction, but it is increasingly becoming a topic of serious scientific discussion. The technological challenges are immense, but the potential rewards are equally vast. The colonization of other planets in the Milky Way could serve as a way to ensure the long-term survival of humanity. Earth, while currently hospitable, is vulnerable to a variety of existential threats, including climate change, asteroid impacts, and supervolcanoes. By establishing colonies on other worlds, we could create a form of insurance for the human race, ensuring that civilization continues even if Earth were to become uninhabitable. Mars is often cited as the most likely candidate for human colonization. Its proximity to Earth, along with the presence of water ice and the possibility of terraforming, make it an attractive target for future exploration and settlement. Other moons and planets in the solar system, such as Europa, Titan, or even Venus, could also be potential candidates for human expansion, though they would present greater challenges in terms of habitability. Beyond the solar system, the colonization of planets in other star systems would require advances in propulsion technology that far exceed anything we have today. While current spacecraft can travel at only a fraction of the speed of light, theoretical concepts such as nuclear propulsion, ion drives, and even warp drives could one day make interstellar travel a reality. If humanity can overcome these challenges, the stars of the Milky Way could become our new frontier, with colonies spread across the galaxy. The ethical implications of becoming a galactic civilization are significant. How should we treat the environments of other planets? What rights do we have to alter or exploit these worlds? And what happens if we encounter other intelligent species along the way? These are questions that humanity will need to grapple with as we move toward a future where the Milky Way is not just a distant object in the sky, but a place we can explore, settle, and thrive in. The Milky Way as a mirror of the universe. In many ways, the Milky Way is a microcosm of the universe itself. The forces and processes that shape our galaxy, gravity, dark matter, star formation, and cosmic evolution, are the same forces that govern the entire cosmos. By studying the Milky Way, we gain insights into the broader workings of the universe, from the formation of stars and galaxies to the mysteries of dark matter and the fate of the cosmos. The Milky Way is also a reminder of the interconnectedness of all things. The stars, planets, and even the atoms in our bodies are all part of a larger cosmic story, one that has been unfolding since the birth of the universe. The heavy elements that make up the Earth and everything on it were forged in the hearts of stars, and the same processes that created the Milky Way continue to shape galaxies across the universe. In this sense, the Milky Way serves as both a window and a mirror. It is a window into the broader universe, allowing us to study the forces that shape galaxies and the nature of the cosmos itself. But it is also a mirror, reflecting back to us the fundamental truths about our place in the universe, that we are part of a vast, interconnected web of matter and energy, stretching across space and time. The Milky Way, a story of wonder and exploration. As we continue to explore the Milky Way, we are constantly reminded of its beauty, complexity, and mystery. From the majestic spiral arms to the hidden depths of the galactic center, the Milky Way is a place of endless discovery, where each new observation reveals more about the galaxy we call home. The journey of understanding the Milky Way is far from over. As new technologies and missions come online, we will continue to probe deeper into the heart of the galaxy, uncovering its secrets and expanding our knowledge of the universe. From studying the formation of stars and planets to searching for life beyond Earth, the Milky Way will remain at the center of our quest to understand the cosmos. Yet, as much as we learn about the Milky Way, the galaxy also reminds us of the limits of human knowledge. For every answer we find, new questions emerge, leading us deeper into the mysteries of existence. The galaxy's vastness humbles us, but it also inspires us to keep exploring, to keep asking questions, and to continue seeking our place in the universe. In the end, the Milky Way is more than just a collection of stars and planets, it is a symbol of the human spirit's drive to explore, to understand, and to find meaning in the cosmos. It is a reminder that, no matter how small we may seem in the grand scale of the universe, we are part of something extraordinary, a cosmic story that has been unfolding for billions of years and will continue for billions more. As we look up at the night sky, we are reminded that the Milky Way is not just out there, it is here, with us, a part of us, and a part of the endless wonder that is the universe. The Milky Way's legacy, stars, planets, and the continuation of life. As we look toward the future, the Milky Way's legacy lies not just in the past and present but also in its potential to foster life, star systems, and the evolution of new worlds for eons to come. Stars will continue to be born in the galaxy's nurseries, and planets will emerge around them, creating new environments where the story of life might play out once again. The galaxy itself is a vast, self-sustaining engine of creation and destruction, where matter is recycled through cosmic processes, giving rise to new generations of stars and planets. The future of life within the Milky Way is bound to the cycles of star formation and the availability of planetary environments that can support life. As long as the galaxy retains its interstellar medium, vast clouds of gas and dust that serve as the raw material for star formation, the potential for new stars and planets remains. Although the Milky Way is slowly depleting its reservoir of gas over time, the process of star birth will continue for billions of years. And with each new star that forms, there arises the possibility that planets orbiting those stars may harbor conditions favorable to life. The most immediate prospects for life lie within the planetary systems we already know about. In recent years, the discovery of planets in the habitable zones of their stars, regions where liquid water could potentially exist, has sparked intense excitement. Worlds like Proxima Centauri b, orbiting the closest star to the Sun, and TRAPPIST-1, a system of Earth-sized planets orbiting a cool red dwarf star, have been identified as potential candidates for further study in the search for life. If life exists on any of these planets, it would represent a profound revelation about the abundance of life in the universe. In the long term, life may face significant challenges as the galaxy evolves. The eventual collision with the Andromeda Galaxy will lead to significant upheavals within the Milky Way. Although the process will unfold over billions of years and will be largely imperceptible to any life forms existing at the time, the merger will alter the structure of the galaxy and potentially trigger new waves of star formation as gas clouds are compressed and disrupted by gravitational forces. The resulting elliptical galaxy, often referred to as Milkomeda, will inherit the combined star systems of the Milky Way and Andromeda, creating a larger, more massive galaxy. However, even as star formation continues into the distant future, the long-term fate of the Milky Way is intertwined with the fate of the universe itself. As the universe expands, it will become increasingly cold and dark, a scenario sometimes referred to as the heat death. In this distant future, when most stars have burned out and the universe is dominated by dark energy, the Milky Way, or whatever remains of it, will be a faint shadow of its former self. Stars will have died out, and black holes will dominate the cosmic landscape. However, even in this distant, cold universe, the remnants of life and the legacy of the Milky Way may still persist in some form. The galactic center, a window into the unknown. The center of the Milky Way is one of the most mysterious and dynamic regions in the galaxy, home to powerful forces that shape the galaxy as a whole. At its heart lies the supermassive black hole, Sagittarius A*, which exerts a profound influence on the surrounding stars and gas. This black hole, with a mass of over 4 million suns, is the gravitational anchor of the entire galaxy, around which all of its stars orbit. The area around Sagittarius A* is a hotbed of activity, with stars moving at breakneck speeds as they orbit the black hole, and gas clouds being heated to millions of degrees as they spiral inward. Occasionally, a star or gas cloud ventures too close to the black hole and is torn apart by its intense gravitational pull. When this happens, the material is stretched and compressed, emitting bursts of energy as it is consumed by the black hole. This violent process provides astronomers with valuable insights into the behavior of black holes and the extreme physics that govern them. While black holes themselves are invisible, since not even light can escape their gravitational pull, the effects of their presence can be seen in the orbits of nearby stars and the radiation emitted from their surroundings. Sagittarius A* remains relatively quiet compared to the black holes in other galaxies, which can emit vast amounts of energy as they consume matter, but it is far from dormant. Occasionally, bursts of X-rays and radio waves indicate that the black hole is accreting material, providing a glimpse into the otherwise hidden processes occurring in this distant, enigmatic region. The galactic center is also home to some of the densest star clusters in the galaxy. These clusters, packed with stars in close proximity, experience intense gravitational interactions that shape their orbits and evolution. Stars in this region can be flung out of the cluster at high velocities or drawn into the gravitational influence of the black hole. Studying these star clusters provides astronomers with a unique laboratory for understanding how stars evolve in extreme environments. One of the key questions astronomers hope to answer is how supermassive black holes like Sagittarius A* form and grow over time. While it is clear that such black holes play a central role in the evolution of galaxies, the process by which they acquire their immense mass is still not fully understood. Some theories suggest that they grow through the merger of smaller black holes, while others propose that they form from the collapse of massive clouds of gas early in the universe's history. Understanding the life cycle of black holes will shed light on the broader question of how galaxies like the Milky Way form and evolve. The cosmic frontier, humanity's role in the future of the Milky Way. As humanity ventures further into the cosmos, the Milky Way itself becomes a new frontier, one that offers endless opportunities for discovery, exploration, and the continuation of life beyond Earth. The next few centuries will likely see the establishment of permanent outposts on the Moon and Mars, as well as robotic missions to the outer planets and their moons. These early steps into the galaxy will pave the way for more ambitious ventures, including the exploration of nearby star systems and, eventually, interstellar travel. The development of advanced propulsion technologies could one day allow humans to travel to the nearest stars. Concepts like nuclear fusion propulsion, solar sails, and even theoretical warp drives offer tantalizing possibilities for reaching distant planets within the Milky Way. If humanity succeeds in developing these technologies, the galaxy could become our new home, with colonies and civilizations spread across the stars. However, with this expansion comes the responsibility to preserve the Milky Way's natural beauty and protect the environments we encounter. As we explore the galaxy, we must remain mindful of the potential impact of our actions on other worlds and the ecosystems they may harbor. Planetary protection protocols will become increasingly important as we venture into new environments, ensuring that we do not inadvertently contaminate or destroy potential habitats for life. The ethical implications of galactic exploration extend beyond just the physical impact on planets and moons. As we encounter new worlds and possibly new forms of life, we will need to consider how we interact with these discoveries. Should we colonize planets that are already inhabited by microbial life, or should we preserve them as natural reserves? How should we engage with intelligent civilizations if we encounter them? These questions are complex, and their answers will shape the future of humanity in the Milky Way. At the same time, the exploration of the Milky Way offers immense opportunities for scientific discovery. Studying distant star systems and exoplanets could provide new insights into the formation of planetary systems and the conditions required for life. Exploring the outer reaches of the galaxy could help us understand the nature of dark matter and dark energy, the invisible forces that dominate the universe. And as we explore, we will continue to deepen our understanding of the fundamental forces that govern the cosmos, from the birth of stars to the evolution of galaxies. The infinite horizon, what lies beyond the Milky Way? While the Milky Way is our immediate cosmic neighborhood, it is just one of billions of galaxies that make up the universe. Beyond the boundaries of our galaxy lies a vast, unexplored realm, filled with galaxies, galaxy clusters, and cosmic structures that extend far beyond what we can currently observe. The study of these distant galaxies provides us with a glimpse into the universe's past, as the light from these galaxies has taken billions of years to reach us, showing us the universe as it was in its infancy. The ultimate fate of the Milky Way is tied to the larger universe. As the universe continues to expand, galaxies will move farther apart, and the cosmic landscape will change. In the distant future, the universe may become a cold, dark place, with galaxies isolated from one another by the expansion of space. Stars will burn out, and black holes will dominate the cosmos, slowly evaporating through a process known as Hawking radiation. However, even in this far-off future, the legacy of the Milky Way will endure. The stars, planets, and life that originated within the galaxy will have left their mark on the universe. Whether through the continued exploration of the galaxy by future civilizations or the remnants of human technology and culture left behind on distant planets, the Milky Way will remain a symbol of our journey through the cosmos. The exploration of the Milky Way, and the universe beyond, is an ongoing adventure, one that will continue for millennia. As we uncover new mysteries and answer old questions, we are reminded that the universe is vast, complex, and full of wonder. The Milky Way is not just a distant collection of stars, it is our home, our past, and our future. It is the place where we were born, the place where we seek to understand the universe, and the place where the story of life in the cosmos unfolds. In this grand cosmic journey, the Milky Way stands as a beacon of exploration, discovery, and the enduring quest to know our place in the universe. As long as we continue to look up at the stars, we will be reminded of the infinite possibilities that await us, both within our galaxy and beyond. The cosmic dance, interactions between galaxies in the Milky Way's neighborhood. While the Milky Way is vast and complex in its own right, it exists within an even larger framework of galaxies that populate the local group, a collection of galaxies bound together by gravity. The Milky Way's closest companion is the Andromeda Galaxy, which, as we know, is on a collision course with our own galaxy. But the local group contains many more members, including dozens of smaller dwarf galaxies that orbit the larger ones, each playing a part in the ongoing cosmic ballet that has shaped and will continue to shape the structure of the Milky Way. Among these smaller galaxies are the Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere. The large and small Magellanic Clouds are gradually being pulled apart by the gravitational forces of the Milky Way, and streams of gas and stars connect them to our galaxy. Over time, they will be absorbed into the Milky Way, adding their stars, gas, and dark matter to our growing galactic structure. This process is part of a larger phenomenon known as galactic cannibalism, where larger galaxies absorb smaller ones, growing and evolving as a result. While the Magellanic Clouds are visible reminders of our galactic neighbors, many of the Milky Way's companions are much fainter and more difficult to detect. Dwarf spheroidal galaxies, such as the Sagittarius Dwarf Galaxy, are slowly being torn apart by the Milky Way's gravity, their stars forming long tidal streams that wrap around the galaxy. These streams are relics of past mergers and provide evidence of the Milky Way's dynamic history, revealing how it has grown over billions of years through the gradual accretion of smaller galaxies. The interaction between galaxies is not limited to the local group. Beyond our immediate galactic neighborhood lies the Virgo cluster, a massive collection of thousands of galaxies that dominates the local region of space. The Milky Way and its companions are moving toward the Virgo cluster, though it is unlikely that we will ever merge with it, as the expansion of the universe will eventually pull galaxies farther apart, preventing such large-scale mergers from occurring. These interactions between galaxies, whether through mergers, tidal disruptions, or the exchange of gas and stars, are fundamental to the evolution of the Milky Way. They fuel star formation, drive the growth of dark matter halos, and shape the overall structure of the galaxy. By studying these interactions, astronomers gain insights into the life cycles of galaxies and the forces that govern their behavior on cosmic scales. Dark matter and the Milky Way's hidden structure. One of the greatest mysteries surrounding the Milky Way is the nature of dark matter. While dark matter does not emit, absorb, or reflect light, its gravitational influence is undeniable. It plays a crucial role in holding the galaxy together, particularly in the outer regions where the visible matter alone would be insufficient to account for the observed rotation speeds of stars. Dark matter is thought to form an extended halo around the Milky Way, enveloping the galaxy in a vast, invisible sphere that contains far more mass than all the stars, gas, and dust combined. This dark matter halo not only binds the galaxy together but also influences its interactions with neighboring galaxies and the larger cosmic web. Without dark matter, the Milky Way's stars would not orbit as they do, and the galaxy's spiral structure would not be stable. The exact composition of dark matter remains one of the most pressing questions in modern astrophysics. Several theories have been proposed, including the possibility that dark matter is made up of weakly interacting massive particles, WIMPs, sterile neutrinos, or other exotic particles that interact only through gravity and the weak nuclear force. Despite decades of research, dark matter has yet to be directly detected, though numerous experiments are underway to search for evidence of its existence. While dark matter is invisible to telescopes, its presence can be inferred through gravitational lensing, a phenomenon in which light from distant objects is bent by the gravitational pull of dark matter. This effect has allowed astronomers to map the distribution of dark matter in the Milky Way and other galaxies, revealing the extent of these massive halos. In the future, more precise measurements of gravitational lensing could help scientists better understand the properties of dark matter and its role in shaping the universe. Dark matter also plays a key role in galaxy formation. In the early universe, dark matter clumped together to form the first gravitational wells, into which ordinary matter, hydrogen and helium, fell, leading to the formation of the first stars and galaxies. The Milky Way itself likely formed within a dark matter halo, and its subsequent growth was influenced by the distribution and behavior of dark matter throughout cosmic history. Understanding the nature of dark matter will not only unlock the secrets of the Milky Way but also provide insights into the fundamental structure of the universe. As we continue to probe the hidden components of the galaxy, we are reminded that the Milky Way, like the rest of the cosmos, is shaped by forces that we are only just beginning to understand. The Milky Way's spiral arms, star formation engines. The Milky Way's spiral arms are some of its most distinctive features, curving gracefully through the galactic disk and serving as the sites of intense star formation. These arms are not static structures, they are shaped and maintained by density waves, regions of higher density that move through the galaxy like ripples in water. As gas clouds pass through these density waves, they are compressed, triggering the formation of new stars. The spiral arms are home to some of the galaxy's most beautiful and dynamic regions, including stellar nurseries where massive clouds of gas collapse under gravity to form clusters of new stars. The Orion Arm, a minor spiral arm where our solar system resides, is one such region, containing vast molecular clouds that continue to give birth to stars. The most famous of these is the Orion Nebula, a glowing cloud of gas and dust that can be seen with the naked eye. Star formation in the spiral arms is a cyclical process. As new stars are born, they heat the surrounding gas and light up the nebulae, creating regions of bright, glowing gas. Massive stars, which burn through their fuel quickly, end their lives in supernova explosions, dispersing heavy elements into the interstellar medium. These elements enrich the gas clouds, providing the building blocks for future generations of stars and planets. The spiral arms are also home to some of the Milky Way's largest star clusters, including open clusters and associations of young, hot stars. These clusters are often loosely bound by gravity and gradually disperse over time as their stars move apart. Many of the stars in the Milky Way, including the Sun, likely formed in such clusters before being ejected into the wider galaxy. While the spiral arms are regions of active star formation, they also contain older stars that have migrated outward from the galactic center. As stars orbit the galaxy, they move in and out of the spiral arms, their paths influenced by the gravitational forces of the density waves. This migration, known as radial mixing, helps to spread stars and gas throughout the galactic disk, ensuring that the Milky Way remains a dynamic and evolving system. The Milky Way's future, beyond the Andromeda collision. The collision between the Milky Way and the Andromeda galaxy, set to occur in about 4.5 billion years, will mark a dramatic chapter in the future of our galaxy. But even after this event, the story of the Milky Way will continue to unfold. The merger will create a new, larger galaxy, likely elliptical in shape, with a central supermassive black hole formed from the combination of Sagittarius A** and Andromeda's black hole. While the merger will disrupt the spiral arms of both galaxies, it will also trigger new waves of star formation as gas clouds collide and compress. Many stars, including the Sun, will be thrown into new orbits, and some may even be ejected from the galaxy entirely. Over time, the chaotic interactions will settle into a new, stable structure, and the combined galaxies will continue their journey through the universe as one. In the far future, long after the merger with Andromeda, the Milky Way's fate will be shaped by the evolution of the universe itself. As the expansion of the universe accelerates, driven by dark energy, galaxies will move farther apart, and the larger structures of the cosmic web will gradually break down. The Milky Way, now part of a larger elliptical galaxy, will become increasingly isolated, cut off from other galaxies by the expanding voids of space. As star formation slows and the galaxy's gas reserves are depleted, the Milky Way will enter a quiescent phase, where no new stars are born. The remaining stars will gradually burn out, leaving behind white dwarfs, neutron stars, and black holes. Over trillions of years, even these remnants will cool and fade, and the galaxy will become a dark, quiet place. In the distant future, black holes will dominate the galaxy, slowly evaporating through Hawking radiation. The universe will continue to expand and cool, eventually reaching a state where all matter has been dispersed and no energy remains to fuel stars or galaxies. This ultimate fate, sometimes referred to as the heat death of the universe, will mark the end of the Milky Way's long and storied existence. Yet, even as the stars burn out and the galaxy fades, the legacy of the Milky Way will endure. The stars, planets, and life that emerged within its spiral arms will have left their mark on the universe. Whether through the remnants of ancient civilizations or the continued exploration of the galaxy by future beings, the story of the Milky Way will be part of the larger cosmic narrative, a testament to the beauty and complexity of the universe. The eternal wonder of the Milky Way. As we continue to explore the Milky Way, we are reminded of the infinite wonders it contains. From the dense star clusters at the galactic center to the quiet, distant reaches of the halo, the Milky Way is a place of beauty, complexity, and mystery. It is a galaxy where stars are born, live out their lives, and die in spectacular explosions, and where planets form, evolve, and possibly harbor life. The journey to understand the Milky Way is one that will never end. As we develop new technologies and expand our reach into the cosmos, we will continue to uncover the secrets of our galaxy, deepening our knowledge of the forces that shape it and the life it contains. The Milky Way is not just a distant collection of stars, it is our home, our origin, and our future. In the grand scheme of the universe, the Milky Way is just one of countless galaxies, each with its own story to tell. Yet, for us, it holds a special significance. It is the place where humanity was born, where we have lived and evolved, and where we continue to seek our place in the cosmos. As we look up at the stars, we are reminded that we are part of something much larger than ourselves, a galaxy that has existed for billions of years and will continue to evolve for billions more. The Milky Way is a symbol of the endless possibilities that await us as we explore the universe. It is a reminder that, no matter how vast and mysterious the cosmos may seem, we are connected to it in profound and meaningful ways. The journey to understand the Milky Way is a journey to understand ourselves, our origins, and our place in the grand tapestry of the universe. The Milky Way's quiet outskirts, the galactic halo and its secrets. Beyond the bright, bustling regions of the Milky Way's spiral arms lies a much quieter, more mysterious expanse, the galactic halo. This vast, spherical region extends far beyond the disk of the galaxy, enveloping the Milky Way in a halo of stars, gas, and dark matter. The halo is not as dense or as visually striking as the spiral arms, but it is an integral part of the Milky Way's structure and evolution. In many ways, it is the repository of the galaxy's oldest stars and the remnants of ancient galactic mergers, holding the keys to understanding the Milky Way's past. The stars in the halo are some of the oldest in the galaxy, and many of them are thought to have formed in smaller, satellite galaxies that were absorbed by the Milky Way billions of years ago. These stars, often found in globular clusters, are tightly bound groups of hundreds of thousands of stars, orbiting the Milky Way in elongated orbits that carry them far from the galactic center. Globular clusters are ancient relics of the galaxy's early history, and studying them provides astronomers with valuable insights into the conditions that existed when the Milky Way was still young. The halo also contains stellar streams, long, thin trails of stars that are the remnants of dwarf galaxies torn apart by the Milky Way's gravitational forces. These streams form intricate patterns across the sky, tracing the orbits of the stars that once belonged to separate galaxies. By mapping these stellar streams, astronomers can reconstruct the history of past galactic mergers, revealing how the Milky Way grew over time by absorbing smaller galaxies. In addition to stars, the halo contains a significant amount of dark matter. In fact, most of the Milky Way's mass resides in the halo, in the form of dark matter that exerts a powerful gravitational influence on the galaxy's stars and gas. This dark matter halo extends far beyond the visible boundaries of the Milky Way, providing the gravitational pull needed to hold the galaxy together. Without dark matter, the stars in the outer regions of the galaxy would drift away into intergalactic space, and the Milky Way's spiral structure would unravel. Despite its importance, the galactic halo remains one of the least understood regions of the Milky Way. The stars in the halo are faint and sparsely distributed, making them difficult to observe, and the dark matter that dominates the halo is invisible to telescopes. However, By studying the motion of stars in the halo and using techniques such as gravitational lensing, astronomers are beginning to piece together the structure of the halo and uncover its secrets. The galactic center, a hub of activity and extremes. While the galactic halo is a quiet and sparsely populated region, the center of the Milky Way is a bustling hub of activity, dominated by the intense gravitational pull of the supermassive black hole, Sagittarius A star. This black hole, located about 27,000 light-years from Earth, has a mass of over 4 million suns and is the anchor around which the entire galaxy revolves. The region around Sagittarius A** is one of the most extreme environments in the Milky Way, where stars are packed together in dense clusters and gas clouds are heated to millions of degrees. One of the most striking features of the galactic center is the tight cluster of stars that orbit close to Sagittarius A star. These stars, known as S-stars, travel at incredible speeds, completing orbits around the black hole in just a few years. Their rapid motion provides direct evidence of the black hole's immense gravitational pull, and their orbits are used to measure the mass of Sagittarius A** with remarkable precision. The galactic center is also home to massive clouds of gas and dust, some of which are slowly being drawn toward the black hole. As these clouds spiral inward, they are heated to extreme temperatures, emitting X-rays and other forms of high-energy radiation. Occasionally, a gas cloud or star will venture too close to the black hole and be torn apart by tidal forces, its material stretched and compressed as it falls into the black hole. These events, though rare, provide valuable insights into the behavior of matter in the vicinity of black holes and the extreme physics that govern these regions. In addition to Sagittarius A**, the galactic center contains a dense concentration of stars, many of which are part of the galactic bulge, a spherical region of older stars that surrounds the center of the galaxy. The stars in the bulge are packed much more tightly than those in the spiral arms, and their orbits are influenced by the gravitational forces of both the black hole and the surrounding mass of the galaxy. The galactic bulge is thought to have formed early in the Milky Way's history, and studying its stars provides clues about the conditions that existed during the galaxy's formation. The birthplaces of stars, nebulae and molecular clouds. One of the most remarkable features of the Milky Way is its ability to continuously give birth to new stars. This process occurs in regions known as nebulae and molecular clouds, where vast quantities of gas and dust collapse under the force of gravity, forming dense clumps that eventually ignite as new stars. These stellar nurseries are scattered throughout the spiral arms of the galaxy, creating beautiful and dynamic regions of star formation. One of the most famous star-forming regions in the Milky Way is the Orion Nebula, a bright and colorful cloud of gas located about 1,300 light-years from Earth. The Orion Nebula is home to hundreds of young stars, many of which are still in the process of forming. These stars are surrounded by protoplanetary disks, rotating disks of gas and dust that may one day give rise to planets, moons, and other celestial bodies. The process of star formation begins when a region of a molecular cloud becomes dense enough for gravity to overcome the pressure of the gas. As the gas collapses, it heats up, forming a protostar, a young star that has not yet begun nuclear fusion. Over time, the temperature and pressure in the core of the protostar increase, eventually reaching the point where hydrogen atoms begin to fuse into helium, releasing vast amounts of energy. At this point, the protostar becomes a full-fledged star, radiating light and heat into the surrounding space. Star formation is often a violent process, with powerful stellar winds and intense radiation from newly formed stars carving out cavities in the surrounding gas. Massive stars, in particular, have a profound impact on their environments, emitting high-energy ultraviolet light that ionizes the gas and creates glowing regions known as HII regions. These regions are some of the most beautiful and recognizable features of the Milky Way, with intricate patterns of light and shadow sculpted by the forces of star formation. Massive stars also live fast and die young, ending their lives in supernova explosions that seed the galaxy with heavy elements. These explosions not only enrich the interstellar medium with the building blocks of planets and life but also trigger new waves of star formation by compressing nearby gas clouds. In this way, The death of one generation of stars fuels the birth of the next, ensuring that the Milky Way remains a vibrant, evolving system. The Milky Way's satellite galaxies, cosmic companions. The Milky Way is not an isolated structure but is surrounded by a host of smaller satellite galaxies that orbit it like moons around a planet. These satellite galaxies are much smaller than the Milky Way, but they play an important role in its evolution, providing fresh material for star formation and influencing the galaxy's overall structure. The two most prominent satellite galaxies are the Large and Small Magellanic Clouds, which are visible to the naked eye from the southern hemisphere. These irregular dwarf galaxies are currently interacting with the Milky Way, with streams of gas and stars being pulled from them by the larger galaxy's gravitational forces. Over time, the Magellanic Clouds will be fully absorbed into the Milky Way, adding their stars and gas to the galaxy's mass. In addition to the Magellanic Clouds, the Milky Way is surrounded by several dozen other dwarf galaxies, some of which are in the process of being torn apart by the Milky Way's gravity. The Sagittarius dwarf galaxy, for example, is currently being shredded by tidal forces, and its stars are forming long streams that wrap around the Milky Way. These tidal streams are the remnants of past galactic mergers and provide evidence of the Milky Way's dynamic history. The satellite galaxies are not just passive companions, they actively shape the Milky Way's evolution. The gravitational interactions between the Milky Way and its satellites can trigger bursts of star formation by compressing gas clouds in the spiral arms. These interactions also help to build up the Milky Way's dark matter halo, as the satellite galaxies contribute their own dark matter to the larger structure. The study of satellite galaxies is crucial for understanding the Milky Way's growth over time. By tracing the orbits of these galaxies and studying the tidal streams they leave behind, astronomers can reconstruct the history of galactic mergers and gain insights into how the Milky Way became the massive spiral galaxy we see today. The future of the Milky Way, a galaxy in transition. The Milky Way's future is one of constant change. Over the next few billion years, the galaxy will continue to evolve, shaped by its interactions with nearby galaxies and the forces of gravity and dark matter. The most dramatic event in the Milky Way's future is the impending collision with the Andromeda Galaxy, which is set to occur in about 4.5 billion years. When the Milky Way and Andromeda collide, their spiral structures will be disrupted, and the resulting galaxy will likely take on a new, elliptical form. The collision will trigger intense bursts of star formation as gas clouds are compressed by gravitational forces, and many stars will be thrown into new orbits or ejected from the galaxy entirely. The central black holes of both galaxies will eventually merge, forming a supermassive black hole even more massive than Sagittarius A star. Although this galactic collision will mark a significant transformation for the Milky Way, it is just one step in the galaxy's long evolution. As the universe continues to expand, galaxies will become more isolated, and star formation will gradually come to an end. In the far distant future, the Milky Way will enter a quiescent phase, where no new stars are born, and the remaining stars slowly burn out and fade away. But even as the Milky Way transitions into this quieter state, its legacy will endure. The stars, planets, and life that emerged within its spiral arms will have left their mark on the universe, and the galaxy's story will continue to be told by future civilizations, whether they remain on Earth or spread across the stars. The Milky Way, a cosmic wonder. The Milky Way is more than just a galaxy, it is a symbol of the wonder and mystery of the universe. It is a place of unimaginable beauty and complexity, where stars and planets are born, live, and die in a grand cosmic cycle. As we continue to explore and study the Milky Way, we are reminded of our connection to the cosmos and the profound role that our galaxy plays in shaping the universe. The Milky Way is our home, our origin, and our future. It is the place where humanity has lived out its history, and it is the place where we will continue to seek answers to the most fundamental questions about the nature of existence. As we look up at the stars and contemplate the vastness of the galaxy, we are reminded that we are part of something much larger than ourselves, a grand cosmic story that has been unfolding for billions of years and will continue to evolve for billions more. In this story, the Milky Way is a central character, a galaxy that has given birth to stars, planets, and life, and that will continue to shape the universe for eons to come. The Milky Way and the search for extraterrestrial life. The Milky Way, with its billions of stars and even more planets, presents an incredible opportunity for the search for extraterrestrial life. As we peer deeper into our galaxy, one of the most profound questions we face is whether life exists beyond Earth. The vast diversity of planetary systems within the Milky Way suggests that the ingredients for life may not be unique to our planet, raising the tantalizing possibility that life could be more common than we once thought. For centuries, humanity has looked to the stars and wondered if we are alone in the universe. Today, thanks to advancements in astronomy, exoplanet discovery, and the study of astrobiology, we are closer than ever to answering this question. The search for life in the Milky Way has shifted from mere speculation to scientific inquiry, driven by discoveries of planets in the habitable zones of their stars, regions where conditions might be right for liquid water to exist, a key ingredient for life as we know it. One of the most exciting developments in this field has been the discovery of exoplanets orbiting stars throughout the Milky Way. Missions like NASA's Kepler Space Telescope and its successor, the Transiting Exoplanet Survey Satellite, TESS, have identified thousands of planets orbiting stars of various types, many of which lie in their stars' habitable zones. Some of these planets are rocky, Earth-like worlds that could have atmospheres and surface conditions suitable for life. Among the most intriguing discoveries are the planets orbiting red dwarf stars, which are smaller and cooler than the Sun. Red dwarfs are the most common type of star in the galaxy, and many of their planets reside within the habitable zone due to the star's low energy output. While red dwarfs are prone to stellar flares that could strip a planet's atmosphere, the sheer number of these stars means that some of their planets might still have conditions favorable for life. The search for life goes beyond the detection of planets in habitable zones. Astronomers are now focusing on finding biosignatures, chemical indicators of life, in the atmospheres of exoplanets. By analyzing the light that passes through a planet's atmosphere as it transits in front of its star, scientists can identify the presence of molecules such as oxygen, methane, and water vapor, which could indicate biological processes. Future telescopes, like the James Webb Space Telescope, are designed to study the atmospheres of exoplanets in greater detail, bringing us closer to finding evidence of life beyond Earth. Extremophiles, life in extreme conditions. One of the most surprising discoveries of modern biology is the existence of extremophiles, organisms that can survive in some of the most extreme environments on Earth, from deep ocean hydrothermal vents to acidic hot springs and frozen polar regions. The study of extremophiles has expanded our understanding of where life can thrive and has profound implications for the search for life in the Milky Way. Extremophiles show that life is incredibly resilient and can adapt to conditions that were once thought to be uninhabitable. This discovery has led astrobiologists to reconsider the potential for life in environments very different from those on Earth. Planets and moons once considered too hostile for life may, in fact, harbor microbial ecosystems similar to those found in Earth's extreme environments. For example, Europa, one of Jupiter's moons, has a subsurface ocean beneath its icy crust that may contain the necessary conditions for life. Hydrothermal vents on Europa's ocean floor could provide energy sources similar to those that support life around deep-sea vents on Earth. Similarly, Saturn's moon Enceladus has geysers that spew water vapor and organic molecules into space, suggesting the presence of a subsurface ocean that could be hospitable to life. The discovery of extremophiles has broadened the scope of the search for life in the Milky Way, highlighting the possibility that life could exist in environments previously deemed inhospitable. As our understanding of the limits of life grows, so too does our excitement about the potential for discovering alien life within our galaxy. The Fermi paradox: where is everybody? While the discovery of exoplanets and extremophiles has fueled optimism about the possibility of life elsewhere in the Milky Way, it also raises a perplexing question: if life is common in the galaxy, why haven't we found any evidence of it yet? This question, known as the Fermi paradox, was first posed by physicist Enrico Fermi in the 1950s. Despite the vast number of stars and planets in the Milky Way, there is no clear sign of advanced extraterrestrial civilizations. So, where is everybody? There are several possible explanations for the Fermi paradox, each with profound implications for our understanding of life in the galaxy. One possibility is that life is indeed rare and that Earth is one of the few, if not the only, planets in the Milky Way where life has arisen. In this scenario, the conditions that led to the emergence of life on Earth might be extraordinarily rare, making the galaxy largely devoid of biological activity. Another explanation is that while microbial life may be common, the evolution of intelligent life is exceedingly rare. Earth has been home to life for billions of years, but only in the last few million years has a species developed the ability to build civilizations and explore space. It is possible that intelligent civilizations are rare because they require a unique set of circumstances to evolve, or they may exist only for brief periods before becoming extinct due to natural or self-inflicted causes. A more optimistic possibility is that intelligent civilizations do exist but are either too far away for us to detect or have chosen not to communicate with us. The Milky Way is vast, and the distances between stars are immense. Even if an advanced civilization were sending out signals, they might take thousands or millions of years to reach us. Additionally, such civilizations might use technologies that are beyond our current ability to detect, or they may simply have no interest in communicating with other species. The Fermi paradox remains one of the most intriguing mysteries in the search for extraterrestrial life. As we continue to explore the Milky Way and search for signs of life, we may one day find an answer to this paradox, an answer that could fundamentally reshape our understanding of the galaxy and our place within it. SETI, the search for extraterrestrial intelligence. For decades, the search for extraterrestrial intelligence, SETI, has been at the forefront of efforts to detect signs of advanced civilizations in the Milky Way. SETI programs use radio telescopes to listen for signals that could be transmissions from intelligent beings. The idea behind SETI is that if an advanced civilization exists elsewhere in the galaxy, it might be broadcasting radio signals, either intentionally or unintentionally, that could be detected from Earth. The SETI Institute, founded in 1984, has been a leader in the search for extraterrestrial intelligence. By scanning the skies for narrow-bandwidth radio signals, which are unlikely to occur naturally, SETI scientists hope to identify transmissions that could be the work of an advanced civilization. Although no confirmed signals have been detected so far, the search continues, with new technologies and methods being developed to improve the chances of success. One of the challenges of SETI is the sheer scale of the search. The Milky Way contains hundreds of billions of stars, and scanning each one for signals is a monumental task. Furthermore, radio signals weaken as they travel through space, making it difficult to detect faint signals from distant civilizations. Despite these challenges, SETI remains one of the most exciting and speculative fields of astronomy, driven by the hope that one day we might make contact with intelligent beings from another world. In addition to radio signals, SETI researchers are now exploring other potential ways of detecting extraterrestrial intelligence. For example, advanced civilizations might use laser technology to communicate over vast distances, and SETI programs are beginning to search for optical signals that could indicate the presence of such technology. Another possibility is the detection of technosignatures, evidence of technology or large-scale engineering projects, such as Dyson spheres, that could reveal the existence of advanced civilizations. While the search for extraterrestrial intelligence has yet to yield definitive results, the potential for discovery keeps scientists motivated. A successful detection of intelligent life elsewhere in the Milky Way would represent one of the greatest breakthroughs in human history, forever changing our view of the galaxy and our place in the universe. The future of life in the Milky Way. As we continue to explore the Milky Way and search for extraterrestrial life, we must also consider the future of life in our own galaxy. The Milky Way is not static, it is constantly evolving, shaped by the forces of gravity, dark matter, and cosmic expansion. Over the next few billion years, the Milky Way will undergo significant changes, including its eventual collision and merger with the Andromeda Galaxy. This event will trigger a burst of star formation and lead to the creation of a new, larger galaxy. In the distant future, as star formation slows and the galaxy's gas reserves are depleted, the Milky Way will enter a quieter phase of its evolution. The remaining stars will gradually burn out, and the galaxy will become a darker, more tranquil place. However, life, if it still exists at that time, may have adapted to these changing conditions, finding new ways to thrive in the galaxy's twilight. Humanity's role in the future of life in the Milky Way is still uncertain. As we develop new technologies and expand our presence in the solar system and beyond, we may one day spread throughout the galaxy, establishing colonies on distant planets and moons. The exploration of the Milky Way could become a key part of humanity's long-term survival, offering new opportunities for discovery, growth, and the continuation of life. The search for extraterrestrial life, and the quest to understand the Milky Way, is part of a larger journey, one that connects us to the stars and the galaxy that gave us life. As we continue this journey, we are reminded that we are not just inhabitants of Earth, but citizens of the Milky Way, part of a galaxy that stretches across the cosmos and holds the potential for endless discovery and wonder. The Milky Way and human exploration, our place in the cosmos. As we push the boundaries of exploration, humanity's curiosity about the Milky Way continues to grow. The advent of space travel has allowed us to take our first small steps into the galaxy, exploring the planets and moons of our own solar system, with the tantalizing dream of one day reaching the stars. The Milky Way, with its billions of stars and planets, presents both an enormous challenge and a monumental opportunity for human exploration. The idea of humans traveling beyond our solar system, colonizing distant worlds, and perhaps one day becoming a multiplanetary or even multistellar species is one that captivates the imagination. Human exploration of the Milky Way begins with our own cosmic backyard, the solar system. Already, robotic missions have explored the outer planets, and humans have landed on the Moon and sent rovers to Mars. But these achievements represent only the beginning of what is possible. The next few decades are likely to see the establishment of permanent human bases on the Moon and Mars, with plans to mine asteroids, explore the icy moons of Jupiter and Saturn, and send spacecraft deeper into the outer reaches of the solar system. The most ambitious goals of human space exploration involve not just traveling within the solar system but reaching beyond it, to the nearest stars and eventually to distant planets within the Milky Way. One of the most promising targets for future interstellar exploration is Proxima Centauri b, an Earth-sized planet orbiting the star closest to the Sun, Proxima Centauri. Though Proxima Centauri is just over 4 light-years away, the vast distances involved make this journey a daunting challenge, requiring new propulsion technologies that far exceed what is currently available. The challenges of interstellar travel. The vast distances between stars present one of the greatest obstacles to human exploration of the Milky Way. The fastest spacecraft we have today would take tens of thousands of years to reach even the nearest star systems. To make interstellar travel feasible, we will need to develop new forms of propulsion that can achieve speeds far greater than anything currently possible. Several concepts are being explored, each with its own potential to revolutionize space travel. One of the most promising ideas is nuclear fusion propulsion, which would harness the same process that powers the Sun to propel spacecraft at a significant fraction of the speed of light. Fusion reactors could provide the enormous amounts of energy needed to accelerate a spacecraft to high speeds while using relatively small amounts of fuel. However, developing practical fusion propulsion technology remains a significant scientific and engineering challenge. Another concept is the idea of a light sail, which would use a giant, ultra-thin sail to capture the pressure of photons from a powerful laser or from sunlight itself. This method could, in theory, propel a spacecraft to high speeds without the need for onboard fuel. A notable project exploring this idea is Breakthrough Starshot, which aims to send tiny, lightweight spacecraft to the Alpha Centauri system using powerful lasers to accelerate them to a significant fraction of the speed of light. Although this approach is still in the experimental stage, it represents a potential way to explore nearby stars in the not-too-distant future. More speculative concepts, such as the idea of a warp drive, could offer a solution to the problem of vast interstellar distances by allowing spacecraft to effectively bend spacetime, shortening the distance between 2 points. While warp drives are currently only theoretical and rely on principles that are not yet understood or achievable, they remain a fascinating area of research, driven by the desire to overcome the limitations of conventional propulsion. The development of these technologies could transform humanity's ability to explore the Milky Way, opening up new frontiers for discovery and settlement. However, the challenges are immense, and the timeline for achieving interstellar travel may span centuries. Even so, the dream of reaching the stars continues to inspire scientists, engineers, and space enthusiasts alike. Terraforming and colonization, creating habitable worlds. One of the key questions facing humanity as we look to explore and colonize the Milky Way is how we will adapt to environments that are vastly different from Earth. Most planets and moons in the galaxy are unlikely to have Earth-like conditions, meaning that human survival will depend on either creating artificial habitats or modifying the environments of these worlds through a process known as terraforming. Terraforming involves transforming a planet's atmosphere, temperature, and surface conditions to make it more hospitable to human life. Mars, with its relatively moderate conditions compared to other planets, is often seen as the most likely candidate for terraforming within the solar system. By thickening Mars' atmosphere, raising its temperature, and introducing greenhouse gases, scientists believe it may be possible to create conditions that would allow liquid water to exist on the surface and make the planet more suitable for human habitation. While the concept of terraforming is still largely theoretical, advances in climate science, planetary geology, and environmental engineering may one day make it possible to modify the environments of other planets. However, terraforming presents significant ethical and practical challenges. For one, the process would take centuries or even millennia to complete, requiring long-term commitments across generations. Additionally, we must consider the potential impact on any existing ecosystems that might exist on these planets. If microbial life is found on Mars or other worlds, the decision to terraform could have profound implications for how we value and protect alien life forms. In addition to terraforming, human colonization efforts may rely on creating artificial habitats, self-contained ecosystems capable of supporting life in environments that are otherwise inhospitable. Space habitats, such as those envisioned by physicist Gerard K. O'Neill, would involve large, rotating space stations that generate artificial gravity and house entire communities of people. These habitats could be built in orbit around planets, moons, or even asteroids, providing a controlled environment for long-term human settlement. As we explore the Milky Way, the creation of habitable environments, whether through terraforming or artificial habitats, will be a crucial step in expanding human presence beyond Earth. The development of sustainable, self-sufficient colonies will be key to ensuring humanity's long-term survival and success in the galaxy. Ethics and the exploration of the Milky Way. With the promise of exploring and settling distant worlds comes a set of profound ethical questions. How should humanity interact with the environments we encounter in the Milky Way? What responsibilities do we have to protect potential ecosystems, both microbial and advanced, on other planets? And what impact will our expansion into the galaxy have on our understanding of life and our place in the universe? The potential discovery of life on other planets, even if it is microbial, would raise significant ethical dilemmas. If we find life elsewhere, do we have the right to alter or destroy its environment to make it suitable for human habitation? How do we balance the needs of human survival with the need to protect alien ecosystems? These questions are particularly relevant in the context of terraforming and colonization, where the modification of a planet's environment could have irreversible consequences for any existing life. The principle of planetary protection has been established to prevent the contamination of other worlds by Earth-based life forms. This principle guides current space missions, ensuring that spacecraft sent to potentially habitable environments, such as Mars or Europa, are carefully sterilized to avoid introducing terrestrial microbes. As we move forward with plans for human exploration and colonization, the challenge will be to uphold these ethical standards while balancing the practical needs of expanding human presence in the galaxy. The discovery of intelligent extraterrestrial civilizations would present an even greater ethical challenge. How should we communicate with these civilizations, and what responsibilities do we have in such an encounter? If we find evidence of intelligent life, we must consider the potential cultural, social, and technological impacts of making contact. The consequences of such an encounter could be profound, not only for humanity but for the entire galaxy. In addition to questions about life and ecosystems, the ethics of resource extraction and exploitation in the Milky Way must also be addressed. The galaxy is rich in natural resources, from the minerals found in asteroids to the water ice on distant moons. As humanity expands into the Milky Way, the temptation to exploit these resources will be great. However, we must consider the long-term environmental and social impacts of such activities. Responsible exploration and resource use will be key to ensuring that our expansion into the galaxy is sustainable and does not lead to environmental degradation or conflict. The future of humanity in the Milky Way. As we look to the future, the exploration and colonization of the Milky Way offer both incredible opportunities and significant challenges. The Milky Way is a galaxy of immense potential, filled with untold wonders and mysteries waiting to be discovered. From the icy moons of the outer solar system to the distant planets orbiting stars in the galactic disk, the possibilities for exploration and discovery are endless. At the same time, the journey to explore the Milky Way will test humanity's technological capabilities, ethical principles, and willingness to cooperate on a global scale. The development of interstellar propulsion, the creation of sustainable colonies, and the preservation of extraterrestrial ecosystems will require unprecedented collaboration among nations, scientists, and engineers. The decisions we make in the coming decades will shape the future of humanity and determine our place in the galaxy. In the grand scheme of the universe, the Milky Way is our home. It is where humanity was born, and it is where we will take our first steps into the wider cosmos. The exploration of the Milky Way is not just a scientific endeavor, it is a journey of discovery, wonder, and self-reflection. As we explore the stars, we will learn not only about the galaxy but also about ourselves, our values, and our role in the universe. The Milky Way holds the promise of endless discovery, and as we continue to push the boundaries of exploration, we are reminded that we are part of a much larger cosmic story. Whether we find life on distant planets, establish colonies on new worlds, or simply deepen our understanding of the galaxy's structure and history, the Milky Way will remain a source of inspiration and fascination for generations to come.